Hi guys, welcome back. So today we'll be discussing a new part of our physical chemistry lecture series. Previously we discussed equations of state, so now we'll be looking at the bigger picture of thermodynamics. So our approach to this topic will be by law, namely we'll be discussing thermodynamics starting with the first law, which is concerned with the conservation of energy, followed by the second and third laws, and then with a discussion on Gibbs free energy. So let's just start with some definitions, okay? So first, let's define thermodynamics, okay? So traditionally, thermodynamics has been defined as a study of energy and its transformations, okay? So you could see that from the name, okay? So thermo relating to energy and dynamics relating to transformations. In the bigger picture of thermodynamics, however, we can also define it as the study of restrictions on the possible properties of matter or on permissible physical processes. Okay, so thermodynamics, it pretty much tries to establish relationships between the different properties of matter and the way that these properties can be changed after undergoing processes. So recall in our discussion of equations of state, we wanted to establish relationships between pressure, volume, temperature, and number of moles of a system. So we're pretty much describing the properties of matter in a particular state, right? So in the larger picture of thermodynamics, however, we want to relate all the parameters of the system, including its internal energy, entropy, as well as its other properties that we just mentioned. Okay, so why do we want to do this? We want to do this so that we could describe and make predictions about the behavior of a system in terms of its energy as well. So we could start looking not only at the properties of matter, but also the processes that matter undergoes. Okay, so we're going to be looking at changes in the state of matter before and after a process. Okay, so while the study of thermodynamics can get a little bit abstract, in these abstractions of these concepts, we find that we could apply them in many cases. Okay, that is, we have universality. So it pretty much applies to all systems. So the laws that govern how machines and engines run, for example, are the same that governs the reactions that fuel stars, and even the laws that govern biochemistry and biology. Okay, so the laws that govern life, right? Okay, so thermodynamics is a very universal field of study. All right, so before we start, let's proceed with some definitions. In studying thermodynamics, we want to divide the universe into two parts, okay, namely the system and the surroundings, okay? So the system, this is just part of the universe under study, okay? So the rest of the universe that's not in the system is just called the surroundings, okay? So we can divide our system from the surroundings using a wall, okay? So the wall is pretty much a barrier, and the type of wall that we use defines the system's so-called boundary conditions, okay? So let's look at different types of systems that we can have, right? So if we have a wall that is both permeable and diathermal, we will have an open system, okay? So an open system is characterized by a free exchange of matter and energy, okay? So living organisms, they are open systems, okay? So we breathe out and breathe in air, for example, and could easily exchange heat with our surroundings, okay? Other types of systems include a closed system, okay? So if our wall now becomes impermeable, okay, so we no longer have an exchange of matter with our surroundings, but we could still exchange energy. Okay, so most of the simple systems that we'll be talking about in our thermodynamics discussions will be closed systems, okay? So we won't be seeing any change of the amount of matter in our systems for a closed system. Right, so another type of system is an isolated system, okay? So now our wall is going to be impermeable and adiabatic, okay? So there's no exchange of both matter and energy. All right, okay, so let's now look at different types of properties of a system, okay? So overall a property, this is just a macroscopic observable that defines the state of the system. Okay, so we have two major types of these properties, okay? So we have extensive and intensive properties. Okay, so extensive properties, they're just going to be dependent on the amount of matter present. Okay, so for illustrative purposes, let's have this system that is divided into four parts. So overall, if a property is extensive, if we take the property of part 1, part 2, part 3, and part 4, and we sum them all together, okay, the sum of that is going to be the property of the entire system, okay? So mathematically, we could express this as the following. Okay, so property X is an extensive property, so that means the sum of the property of part 1, part 2, part 3, and part 4 is equal to the whole. Okay, so examples of extensive properties include volume, internal energy, enthalpy, entropy, and number of moles. Okay, so we could easily see this with volume. Okay, so if we take the volume of 1, 2, 3, and 4 and we sum them all together, okay, that would give us the total volume of the system. All right, so we also have another type of property, which is the intensive properties. So intensive properties are going to be independent of the amount of matter present. Okay, so again, for illustrative purposes, let's take this system that's divided into 4 parts. Okay, so if we have an intensive property, okay, so if we measure the intensive property of part 1, 2, 3, and 4, okay, they're going to be the same as the property of the whole. So this is going to be in contrast to extensive properties that are additive. So to express this mathematically, okay, so the intensive property of the total system is going to be equal to the intensive property of part 1, part 2, part 3, and part 4. Okay, so that means you could just measure the intensive property of one part of the system and you pretty much get the intensive property of the whole system. Okay, examples of intensive properties include temperature, pressure, density, and molar quantities such as molar volume, molar enthalpy. Okay, so we could use temperature as an example. Okay, so in this particular system, okay, if we measure the temperature in part 1, 2, 3, and 4, the total temperature of the system is not going to be the sum of the individual temperatures that we just measured. Okay, so actually the temperature should be the same in all of these parts of our system, and the temperature of the entire system should also be the same as those taken from the parts. All right, so that is an intensive property. All right, so those are just some terms that we wanted to define before we proceed with our more formal discussion of thermodynamics. Okay, so of course when we start talking about thermodynamics, there's also another thing that we need to define before we go into anything else. That is, what is energy? We use the term energy a lot in everyday life, but of course, what is it exactly? Okay, so a lot of textbooks define energy as the ability to do work. Okay, so of course when you analyze this definition, you start to wonder, okay, what does it mean to do work? Okay, so when we look at the definition of work, however, work is also defined as a method of energy transfer. Okay, so this definition is kind of circular because if we look at this, we're pretty much defining energy as the ability to transfer energy. Okay, so not very informative. Okay, so another definition that we could use is this one by Dave Watson. Okay, so Dave Watson defined energy as a property or characteristic of matter that makes things happen, or in the case of stored or potential energy, has the potential to make things happen. Okay, so by making things happen, we are causing changes. Okay, so changes in properties of our system, like changing the temperature, changing the pressure, changing the volume. Okay, so this is due to energy. Okay, so this is what we're interested in thermodynamics after all. Okay, so we're interested in analyzing changes in the properties of our system after undergoing processes. Okay, so all of these changes are driven by energy. All right, so let's look at this a little bit more closely in terms of our system and our surroundings. Okay, so our system is going to have its internal energy. Okay, so internal energy is symbolized by a capital U. Okay, so internal energy is just the total energy that's in the system. Okay, so changes can happen if we have a transfer of this energy to our surroundings or to other systems. Okay, so we could transfer energy by work for one, or we could also transfer energy by heat. Okay, so let's just do an additional clarification on heat. Okay, so heat is also defined as a method of energy transfer. Okay, so we'll talk about these different ways of energy transfer a little bit more closely later on, but I just want to clarify that heat is not something that a system inherently has. Okay, so heat is commonly used in everyday language as something that an object has. Okay, so for example, when an object is hot, sometimes we say that, oh, it has a lot of heat. Okay, so but keep in mind that it doesn't really make sense in the thermodynamic definition of heat because heat is a process. Okay, it's a method of transferring energy. Okay, it's similar to work. Okay, so we never really say that an object has a lot of work. Okay, what we usually mean by that, however, is that an object has an ability to do work. Okay, similar to what we probably mean by when we say an object has a lot of heat. Okay, we mean that an object has the ability to transfer heat. Okay, so just to clarify the meaning of heat. Okay, so overall, these are two methods to transfer energy. Okay, so when we're transferring this energy, then we're going to be changing the internal energy of this system. Okay, so the change in this internal energy can also be associated with a change in other properties of this system. Okay, so of course, if we're transferring this energy, so it has to go somewhere, we're putting it into the surroundings, right? So the surroundings also has its own internal energy, U. Okay, so since it also has this internal energy, the process could also go in the reverse way. Okay, so that means that the surroundings could also transfer energy as work or heat into the system. Okay, so let's look more closely at this internal energy. What is it exactly? Okay, so we said it was the total energy of the system. Okay, so how do we look at what that is exactly? Okay, so we could divide the internal energy into two major parts. Okay, so we could define internal energy as the total sum of kinetic energy and the total sum of potential energy. Okay, so we talked about kinetic energy before. So kinetic energy is the energy of motion. Okay, so in physics we also have a mathematical description of kinetic energy. Okay, so kinetic energy, this is defined as 1/2 times the mass times velocity squared. Okay, so using this definition, we could also derive units for energy. Okay, so this is 1/2 mass. SI unit of mass is kilograms. SI unit of velocity is meters per second, so this is squared. Okay, so if we divide this into two parts, then so we have 1/2, okay, kilograms. Okay, so let's split off one of the meters over here, meters per second squared times meters. This over here, kilograms meters per second squared, this is your Newton, and you have your meter. Okay, so your Newton meter, this is equivalent to your joules. Okay, so your joule is your energy unit. Okay, so another energy unit that is commonly encountered is your calorie. Okay, so 1 calorie is equivalent to 4.184 joules. Okay, so the calorie, it's actually related to the properties of water. Okay, so it's still used a lot. So you might need to use this unit conversion in some of our calculations. Okay, so keep in mind that the calorie, this is a little bit different from the calorie that we see in our food labels. Okay, so the stuff that we see in our food labels is usually capital C calorie. Okay, so capital C calorie, this is just equivalent to 1 kilocalorie. Alright, so just for clarification on this. Okay, so some labels also use the joule, the kilojoule, as a unit of energy. Alright? Okay, so let's also look at this part over here, our potential energy. Okay, so our potential energy, so there's lots of different types of potential energy. Okay, so our potential energy is just our stored energy. So we could have chemical potential energy, electrical potential energy, nuclear, gravitational, lots of different types of potential energy. Okay, so this is the part that probably makes things a little bit more complicated in determining internal energy of a system. Okay, so there's lots of different types of potential energy, and all these things are very, very hard to measure. Okay, so ultimately, if it's really hard to measure potential energy, it's also very hard to measure our internal energy. Okay, so it's never really possible to get an absolute value of the total internal energy of our system. Okay, but luckily we're not really interested in determining the exact internal energy of our system. Okay, what we're usually interested in, after all, are changes, right? Okay, so we're interested in how our internal energy changes after it undergoes a process. Okay, namely if it undergoes a transfer of this energy as work or heat. Okay, So we're interested in the change in internal energy. Okay, so delta U, which is equal to the internal energy of the final state minus the internal energy of the initial state. Okay, so again, we're not really interested in absolute values of internal energy, but rather changes. Okay, so just to look at this graphically, if we have U initial as our initial state of the system, okay, and it undergoes a process, okay, so say that our final state is down over here, okay, we're just interested in this change over here, okay, the delta U, okay. So if delta U is negative, we have a decrease in our internal energy, and if delta U is positive, we have an increase in our internal energy, okay. So note that U final is in a higher internal energy state, all right. Okay, so same thing goes for surroundings actually. Okay, so we could also have a change in internal energy in our surroundings after this process over here. Okay, so we also have a corresponding delta U for our surroundings. Okay, so if we have our system and it transfers some of its internal energy towards the surroundings, there has to be a relationship between the way that delta U of our system changes and delta U of our surroundings changes. Okay, so intuitively we know that we're transferring some of this energy, right? So it has to go somewhere. So if ever we're decreasing the internal energy of our system, okay, this has to lead to a corresponding increase in the internal energy of our surroundings. Okay, so the change in internal energy of our system is going to be in equal magnitude but opposite sign to that of our surroundings. Okay, so this principle is overall just the first law of thermodynamics. Okay, so the first law of thermodynamics tells us that energy cannot be created nor destroyed. Okay, so it only could be transformed or transferred. So when we're saying transform, that means our energy could take different types of forms. Okay, so it could be in terms of kinetic energy, or it could be in terms of potential energy. Okay, so transferred, okay, meaning that if we have a certain amount of energy being transferred from one system to another, okay, so all of that energy has to be accounted for. Okay, so none of that energy is going to magically disappear. Okay, so this energy transfer could occur through many other ways. It could occur through heat, or it could occur through work. All right. Okay, so let's look at different ways in which we could measure changes in internal energy while keeping in mind the first law of thermodynamics. Okay, so keep in mind again that there's two major ways in which we could change our internal energy of our system. Okay, so that is through a transfer of energy via work or via heat. Okay, so when we're going to be considering changes in energy, let's consider infinitesimally small changes. Okay, so we could represent infinitesimally small changes by differentials. Okay, so let's look at the differential of internal energy, du. Okay, so if we're looking at infinitely small changes in internal energy, okay, so this is going to be the sum in the amount of small work that is being done, as well as the infinitely small heat that is being transferred. Okay, so note that I wrote the differentials of internal energy and for work and for heat in different ways. Okay, so we just need to clarify the difference between these types of differentials. Okay, so for internal energy, okay, so this type of differential, this is called an exact differential. All right, and the differentials for work and for heat, okay, so in thermodynamics we call these inexact differentials. Okay, so we can see the significance of these differences when we start to integrate these differentials. Okay, so when we're integrating, we're going to be integrating from the initial to the final state in order to get the overall change during a process. Okay, so let's try to integrate both these sides. Okay, so we're going to start from the initial. Okay, so that's going to be U initial and then U final. Okay, so in the case when we're trying to integrate inexact differentials, however, okay, so we can't exactly define our initial and our final states. Okay, so ultimately what's going to happen here is that we could get an expression when integrating exact differentials. So this will be U final minus U initial, okay? But for work and for heat, which are inexact differentials, okay, so these are going to be path dependent, okay? So it's going to depend how you're going to be integrating these differentials. So we just write this out as the total work and the total heat during the process, okay? So this over here, we could express this as delta U is equal to W plus Q. Okay, so the change in internal energy is just equal to the work that was done as well as the heat that was transferred. Okay, so why do we have to make this differentiation between exact differentials and inexact differentials? Okay, so this has something to do with state functions. Okay, so we can express differentials as exact differentials if we're dealing with so-called state functions. Okay, so state functions are usually expressed as capital letters. Okay, so this means that they are path independent. Okay, so meaning that if we're evaluating a differential, it only depends on the final and the initial states. So for non-state functions, okay, like heat and for work, these are path dependent. Their quantities are going to depend on the path that it was taken in order to get from the initial state to the final state. Okay, so an analogy for this situation over here is when you're climbing a mountain, okay? So the state function in this case is just the difference in heights, okay? So you started from this low altitude and then you went to a higher altitude, okay? So state functions just care about the final and the initial states, okay? Non-state functions, however, they are going to depend on the way that it took you to get to the initial to the final state, okay? So here's one path. Okay, so this is going to be a different value compared to the longer path that you took for B. Okay, if you went around the mountain rather than going straight up. Okay, so overall the value of Q, it's going to depend on the path that it took for W, and W is going to depend on Q. Okay, so that's why we call them inexact differentials, because we can't exactly get their values without knowing the other quantity. Okay, so to get a more concrete energy-related example, okay, we could use the example of discharging a battery. Okay, so let's assume that these two batteries, they have the same amount of internal energy. Okay, so assume that they're fully charged at first. Okay, so there's two different ways in which you could discharge the battery. Okay, so in one method, okay, so you could just connect it to some copper coil and then you're going to waste all the energy as heat. Okay, so if you connect these two terminals, okay, so all of the energy contained in the battery is just going to be dissipated as heat. Okay, so you're able to reach the initial to the final state just by releasing heat. So the amount of heat, however, that you're going to transfer is going to depend on the amount of work. So in this particular case, there's no work. Okay, so you're able to say that all of the heat is just equal to delta U. Okay, so another way of using up the battery is through useful work. Okay, so you can connect it to an electric fan. Okay, so the electric fan is going to do mechanical work. Okay, however, keep in mind that sometimes your electric fan can also heat up a bit, so some of the energy is going to be lost as heat. So overall, there are two ways in which you used up the energy of the battery. Okay, so you dissipated some of that energy as heat, and you also used some of that energy to do work. Okay, so two different pathways. Okay, so again, the amount of work that you would do over here is going to depend on the amount of heat that you would release. Okay, so again, knowing the amount of work would depend on the amount of heat that you would have done. Okay, so again, these are your non-state functions. Okay, so for the most part, however, work and heat are the only non-state functions that we'll be looking at. Okay, so most of the other parameters that we'll be investigating in our discussions are going to be state functions. All right, so let's look at work and heat a little bit more closely. Okay, so we'll look at different ways in which you could calculate the work done by a system as well as the heat involved in the process. Okay. All right, so let's first look at work. Okay, so from your physics, recall that work is defined as when we apply a force and we cause displacement. Okay, so let's look at infinitely small work being done. Okay, so we have our inexact differential of W. So this is going to be equal to a force applied, okay, and the corresponding infinitely small displacement dx that was done. Okay, so overall we could use this picture over here. Keep in mind that whenever we're doing work, we need to have a displacement. Okay, so a typical physics example is if you're pushing against the wall. Okay, so you're exerting a force against the wall, but since there's no displacement, regardless of all the effort that you're doing in pushing the wall, there's no work because, again, there's no displacement that occurred. Okay. However, if your wall is able to move around a bit, okay, so all that effort of pushing that wall actually led to a displacement, so that means you actually were able to do some work. Okay. So overall, displacement is necessary for work to occur. Okay. So for the most part, the type of work that we'll be investigating will be pressure volume work. Okay. So in our initial treatments of very simple systems, where we will be looking at the expansion and contraction of a gas against an external pressure. Okay, so let's look at this process a little bit more closely. We'll use an example system over here, our ideal gas. Okay, so let's first look at expansion. Okay, so keep in mind that all these principles I'll be discussing for expansion will also apply for contraction. But overall, let's look at this gas system over here inside a container with a movable frictionless piston. Okay, so our initial state is that we have volume 1 at a pressure 1 of the gas at constant temperature. Okay, so the gas is also exposed to this external pressure over here. Okay, so this is the initial state. So keep in mind that the gas is also going to be exerting a force on the sides of the container. Okay, so it's also going to be pushing up against this piston here, right? Okay, so there's also an external pressure pushing down, but the gas is pushing up in the opposite direction. Okay, so if we're interested in looking at an expansion process, okay, so there has to be condition as to the values of the external pressure and the pressure of the gas. Okay, so if our gas is going to expand, this means that the pressure exerted by the gas, the upward force, has to be greater than the downward force of the external pressure. Okay, so overall we mean that in order to have an expansion process, P1 has to be greater than P external. Okay, so if that's the case, we have a net force going upwards that's able to push this piston upwards and increase the volume of the gas. Therefore, we have an expansion process. Okay, so overall we see this displacement over here. Okay, so what can we say now about the final pressure of the gas compared to the constant external pressure over here? Okay, so keep in mind that the gas is going to expand only up until a certain point. Okay, so it's going to expand up until the point where it reaches mechanical equilibrium. Okay, so mechanical equilibrium meaning that the upward force exerted by the gas is just balanced out by the force exerted by the external pressure over here. Okay, so the implications of this is that P2 is now equal to the external pressure. Okay, so keep this in mind. Okay, so always whenever we're doing expansion or contraction, okay, the final pressure of your gas always has to be equal to the external pressure. Okay, so this is the condition for mechanical equilibrium. Okay, so the forces being exerted are now equal, and there's therefore going to be no net movement of this piston. All right. Okay, so let's also investigate how we could evaluate work, okay, in this particular case. All right. Okay, so what is work again? So we defined work as dW is equal to force times displacement. Okay, so let's figure out what this force is exactly. Okay, so keep in mind that we're dealing with pressures, right? So how do we define pressure again? So pressure is defined as a force exerted over an area. Okay, so let's also look at what dx is. Okay, so in this particular case, the displacement is this particular distance over here. Okay, we were able to displace this piston by this distance here. Okay, so let's get an expression for force. Okay, so force, this is going to be equal to PA. Okay, so we could replace PA with one of the pressures over here. Okay, so what's going to be constant in this particular case is the external pressure. Okay, so since we're always interested in looking at the process with respect to the gas, okay, the external pressure is going to be equal to negative P external. Okay, so our force overall is negative P external times the area. Okay, so what is the area exactly? We're talking about the area of the piston over here. Okay, so let's bring these two things together. So dW, this is going to be equal to negative P external times your area times your dx, your displacement. Okay, so note that if we multiply an area by a displacement, so this is a height, right? This is ultimately going to be a volume. Okay, so we could write the work as negative P external times dV. Okay, the change in volume of the gas. All right, so this is overall our expression. Okay, so let's look at this a little bit more closely as well. So again, our expression was dW is equal to negative P external dV. Okay, so let's look at the significance of this negative sign over here. Okay, so if we're doing an expansion process, okay, so again, in our expansion process, okay, the initial pressure, so P1, this was greater than the external pressure, right? So it's your gas that is actually pushing against this piston. Okay, so it's your gas that's doing the work. Okay, so expansion process, this means that your gas is doing work on the surroundings. Okay, so that means that the energy to do work is coming from the internal energy, right? Okay, so let's also look at dV. For an expansion, okay, dV is equal to V final minus V initial, right? Okay, so that means that V final is larger, so that means dV, this is going to be a positive value, okay? So if dV is positive, okay, so that means during an expansion process, that means that our work, this is going to be negative, okay? So this is our notation for work, right? So if our system is doing work, that means the work is going to be negative, okay? So why does this make sense again, okay? So recall again our expression for internal energy. So du is equal to dW plus dQ, okay? So if our gas is doing work, okay, this is going to be negative, okay? So doing work decreases the internal energy of the system, okay? So that makes sense, right? Because where does the energy come from to do work? Okay, it's going to be coming from our internal energy, okay? So it makes sense that the internal energy of the system is going to decrease if the gas is doing work, all right? Okay, so keep in mind that this is the notation that we're going to use, okay, in our discussion for thermodynamics, okay, so some references might use the opposite notation, okay, so there tends to be a different notation for physics and chemistry, but just keep in mind our particular notation, okay, so if the gas is doing work, okay, the sign for work is going to be negative, all right? Okay, so let's get a graphical interpretation for this process, okay? So in our example, we're treating the system as being under a constant temperature. Okay, so we're changing the pressure and the volume of our system, right? Okay, so we have an ideal gas, so that means the gas follows Boyle's law, okay? So Boyle's law tells us the relationship between pressure and volume at constant temperature. So here we have a Boyle's law PV isotherm, all right? So let's check out what's happening over here, okay? So let's draw out what volume 1 might be, okay? So here's volume 1, okay? So the corresponding pressure in the initial state, okay? So let's figure out what that is. Let's draw up a line here. So this is going to be the corresponding pressure at volume 1, okay? And at the constant temperature here, all right? Okay, so in order for an expansion to occur, right, so we said that P1 has to be greater than the external pressure, okay? So let's just set some arbitrary external pressure, okay? So P1 has to be greater than external pressure, so that means the external pressure has to be lower. So let's say that's over here, all right? Okay, so if we're trying to figure out then what the final state is going to be, okay, so we said that the final state is going to be defined by mechanical equilibrium. So that means that the external pressure is going to be equal to the final pressure, P2, okay? So overall, we could figure out what the final state is. This over here, this is going to be pressure 2, okay? So pressure 2, this is going to be defined by a certain volume, volume 2, okay? So this is our expansion process, okay? So let's look again what we said about work, right? dW is equal to negative P external dV, right? Okay, so if we integrate this, okay, with respect to the initial and final states, our work is going to be equal to, so P external is constant, right? So we could take this out of the integral sign. So this is going to be negative P external delta V. okay? So let's look at the graphical interpretation of this, okay? So P external, where's P external? This is right over here, okay? What's delta V? Delta V is right over here, okay? So that means if we multiply P external by delta V, we get like this area, right? So this part over here is actually represented by the area under here. Okay, it's a rectangle, right? So this is the height, that is your, this part here, this is your P external, okay? And then your length is your delta V, okay? So there you have it. We could represent work just by looking at the graph of a pressure and volume curve, okay? So this part over here, this is your work, right? Okay, so let's look now at another process, okay? So we could also do the same treatment for a contraction process, okay? So again, we have our gas inside this container with a frictionless movable piston, and we have this, this constant external pressure being exerted, and of course our system is at, again, constant temperature, okay? So this is just an example. We could always change the conditions later on, okay? So overall, our initial state is V1, P1, right? So we want to have a contraction process, okay? So again, let's consider the pressures, the pressure exerted by the gas, okay, versus the external pressure. Okay, so if we want this piston to be moving down in order to contract the gas, that means that the force going downwards has to be greater than the force going upwards. Okay, so this implies that P external is greater than the initial pressure. Okay, so when we look at what's going to happen afterwards, okay, so we have a contraction process now since this force is greater. Okay, so ultimately it's going to be contracting only up until a certain point. Okay, so this means that P external is going to be equal to the final pressure of our system. All right, okay, so this is pretty much the same treatment again, okay? So regardless of whether it is an expansion or contraction process, okay, the final pressure of your gas has to be equal to the external pressure, okay? So this, again, this is your mechanical equilibrium, okay? The same treatment can be applied, okay? So the displacement that occurs is over here. So we could also write down our work as force times displacement, and ultimately we still get the same expression, okay? So dW is going to be equal to negative P external dV, okay? So in this particular case, on the other hand, okay, so we're doing a contraction process, right? dV is going to be negative. We're decreasing the volume, right? Okay, so overall, the sign for work, okay, so negative times negative is going to be positive, okay? So keep in mind again that what's doing the work here? It's not exactly the gas, but rather it's the surroundings, okay? So ultimately in this case, okay, so let's just write this down again. So dW is equal to negative P external dV. So the change in volume is going to be negative, so our work is going to be positive. Since we're doing a contraction process, okay, so it's the surroundings that is doing the work, okay? So surroundings does work on the system, okay? So the positive sign here makes sense because the energy is being transferred from the surroundings to the system, okay? So that means that we expect that the internal energy of our system is going to increase, okay? So du again is equal to dw plus dq, okay? So in this case, if work is being done on the system, dw is positive, okay? So we expect that this work done on the system is going to cause an increase in our internal energy of our system, okay? So overall, again, we have an energy transfer from the surroundings towards the system. Therefore, the internal energy of our system is expected to increase. Okay, so we could also do the same graphical interpretation of this entire process, okay? So again, let's consider what our initial pressure is, okay? So let's treat our initial pressure as a little lower this time, okay? So let's say that it is over here, okay? So P1, okay? So we have a corresponding volume for that, okay? So our corresponding volume is V1, okay? So we said in order to have a contraction process, the external pressure has to be greater than the initial pressure, okay? So let's say that the external pressure is right here, okay? So we also said something about how the external pressure is going to be equal to the final pressure, okay? So this is our final pressure here, P2. So this corresponds to the volume, the final volume, V2, okay? So we're going from V1 to V2, all right? So we also mentioned how work is equal to negative P external times delta V, right? Okay, so if we're getting a graphical interpretation this time for contraction work, okay, we're looking for a rectangle, right? Okay, so the height of the rectangle is going to be the external pressure, so this is the height, and then the width is going to be equal to the change in volume, delta V, okay? So that means in contrast to expansion work, this over here, this is going to be our contraction work, okay? So larger rectangle, okay? So look at this here. This is our work done during contraction, okay? So it's a lot of work to contract the gas, okay? Okay, so let's look at a little bit of a variation of the constant temperature, constant external pressure expansion process. Okay, so let's check out what happens if we do this in multiple steps. Okay, so say that we want to expand our gas from volume 1 to volume 3, okay? So for our initial state, the initial pressure was over here, right? So this is P1, okay? And then our external pressure is down here. So overall, the work that was done to expand the gas from volume 1 to volume 3 is this shaded rectangle over here, okay? So this is the work. Okay, so what happens, however, if we do this in multiple steps? Okay, so let's try to do this in 2 steps instead of 1 step. Okay, so that means we're going to be introducing a different external pressure for the first step, okay? So let's look at this first step over here, okay? So instead of expanding it directly to volume 3, we're going to expand it first to a volume 2. Okay, so keep in mind that we still have the same initial pressure, right? Okay, so this external pressure is still lower than the initial pressure, but note that's a little higher compared to the one-step process. Okay, so it's a little closer to the initial pressure. But overall, our first step did this amount of work here. Okay, so we went from volume 1 to volume 2. Okay, so we could introduce a second step to go to the final volume. And there we have it. Okay, so overall, we have 1 step here, which did this amount of work. Okay, and then the next step is represented by this shaded rectangle here. Okay, so when we did it in 2 steps, note that the amount of work done by the gas increased, right? Okay, so for a 1-step process, the work is represented by this rectangle here, right? However, if we do it in a 2-step process, a little bit more work, right? So that additional work is represented by this additional shaded region, okay? So let's try to do this in 3 steps, okay? So when we do it in 3 steps, okay, so note that we have 3 external pressures. So note that this external pressure over here started to become closer to our initial pressure, but overall we did more work. Okay, so the gas did more work when it was expanding it in 3 steps. Okay, so 1, 2, 3. Okay, so also note that the area under the curve starts to get shaded more and more. Okay, so you're doing more work when you do it in multiple steps. Okay, so what happens if we keep doing this? Okay, so what happens if we start doing this an infinite number of steps? Okay, so if you do this an infinite number of steps, what do you expect to see under the curve over here? Okay, we expect that the entire region under the curve is going to be shaded, right? So if we do this in an infinite number of steps, okay, the amount of work that you would do would be equivalent to the area under the pressure volume curve, okay? So what can we say about the external pressures for each of these infinite steps, okay? So note again from our previous observations that if you increase the number of steps, the external pressure keeps approaching the initial pressure of the gas, okay? So this is the pressure of the gas, right? Okay, so it comes closer and closer to this. Okay, so overall over here, what we could say here is that this is the initial pressure of the gas, right? Okay, so the initial external pressure was pretty much equivalent to the pressure of the gas. Okay, so we're doing that an infinite number of steps. So if you expand the gas a little bit, the pressure is going to decrease. So the external pressure is also going to adjust to the pressure of the gas in the infinite number of steps. Okay, so in each step of the way, you have mechanical equilibrium that was established. Okay, so the pressure of the gas is always going to be equal to the external pressure of the gas. Okay, so it's kind of weird, right? How when you're doing an expansion process, in each step of the way you had mechanical equilibrium. So mechanical equilibrium means that nothing's going to happen anymore, right? So that's why we call this reversible work. Okay, so each step of the way is reversible. Okay, so it's actually not very realistic to have this whole process happen, but it's a nice theoretical limit as to what could possibly happen when we're doing pressure volume expansion work. All right, so this over here, this represents our maximum work done by the gas during expansion. Okay, so when we're trying to calculate reversible work, okay, it's no longer going to be a rectangle, right? So rather, it's the entire area under this curve, right? Okay, so how do we evaluate this reversible work, okay? So what comes to mind when we're talking about areas under the curve, okay? What comes to mind are integrals, right? Okay, so keep in mind that our equation again for work, this is equal to dW is equal to negative P external times dV. Okay, so the tricky part about this now is that the external pressure is no longer constant for the entire process. Okay, recall again what we said earlier is that when we're doing reversible work, the external pressure constantly adjusts to the pressure of the gas. Okay, so each step of the way we have this condition here. The external pressure is equal to the pressure of the gas. Okay, so how do we express the pressure of the gas? Okay, so we're dealing with an ideal gas in this particular example. Okay, so we could use the ideal gas equation. PV is equal to nRT. Okay, so pressure of the gas, this is equal to nRT over volume. Okay, so we could write our expression for work as negative P gas dV, replace the expression for P gas with our ideal gas expression over here. So ultimately we have dW is equal to negative nRT over V times dV. All right. So if we're integrating this, okay, so we could integrate this from the initial to the final state, okay, so integrating our inexact differential will just give us the absolute value of our work done for the process, okay, and if we're integrating this, however, we're doing it from the initial volume to the final volume, okay, so note that number of moles is constant, okay, in this particular example, and our temperature is also constant, so we're dealing with an isothermal expansion or isothermal PV work, okay? So in this particular example, we have negative nRT outside of the integral sign, dV over V, okay? So VI, VF. Okay, so what's the integral of this? Okay, so recall again that this is going to be your ln. So we could evaluate work, okay? That's right, a little note over here. Work reversible as negative nRT ln VF over VI, okay? So this is our expression for reversible work for an ideal gas at constant temperature, okay? So note the conditions in which we can use this equation, guys, okay? So a lot of people get, just because they see an expression for work, that they use these equations for all cases, okay? But keep in mind that we derive this expression for an ideal gas and for isothermal conditions, reversible work. Okay? Okay, so what happens when we're doing the reverse, however? Okay, so we said how during expansion we had a maximum work. Okay, so what happens when we're doing the reverse? Okay, we're starting from this initial volume going to our final volume, so we're doing a contraction process instead, a compression process. Okay, so if we're doing reversible work, then it's not going to be the maximum work done by the gas, but rather if we're doing a compression, it's going to be the minimum work done on the gas. Okay, so recall again that if we do this in a one-step fashion, okay, so if we start from V1 over here and then we want to get to this final volume over here, okay, so this is our initial pressure, right, for a compression process, okay, and then our external pressure has to be equal to the final pressure, so this is our P external. Work is going to be equal to this large rectangle here, okay? So if we do this in multiple steps, however, okay, so another step, let's introduce this here. Okay, so we have this PV curve over here. Okay, so V1, let's say that this is the intermediate volume and this is the final volume. Okay, so again, our initial pressure is over here, P1, okay, and then our intermediate pressure, this is going to be our P external 1, so that means the work in the first step was this smaller rectangle over here, okay. However, it wants to get to the final volume, right? So that means the final volume corresponds to this second external pressure, okay? So the work for step 2 is going to be this larger rectangle here, right? So the drawing isn't perfect, but you could kind of see that we saved this amount of work done on the gas, right, when we did it in 2 steps. Okay, so if you do it an infinite number of steps, okay, so ultimately you'll shave off the rest of these parts that go beyond the curve, and we get this over here. Okay, so this again, this is the minimum work done on the gas during compression. Okay, so that is your reversible work. Okay, so reversible work, again, keep in mind that your external pressure is going to be equal to the pressure of the gas. Okay, so if you imagine how that's happening, okay, so you have our piston here, right? Okay, so we have our pressure of the gas, external pressure, okay? So in each step of the way, according to reversible work, the pressure exerted by our external pressure, that by our surroundings, is going to be equal to the pressure exerted by the gas. So technically there's no net force, right? So it's kind of weird how somehow we're able to push this expansion while each step of the way we have mechanical equilibrium. Okay, so that means it's actually going to take an infinitely long time for this process to happen. So again, it's just a theoretical limit as to the possible work that could be done for pressure volume expansion or compression. Okay, so but we could still kind of approximate this type of process by doing the process very, very, very slowly, as we can do for this particular example over here. Okay, so we have a certain gas expanding from 250 ml to 750 ml very, very slowly. Okay, so this part over here suggests that we have a reversible process, or at least we could approximate the process as being reversible, and it's at 25 degrees. Okay, so this suggests that we have an isothermal expansion process. Okay, so we want to calculate the work involved when the gas behaves ideally. Okay, so that means we could use the equation that we just derived earlier. Okay, so we said that work overall, this is equal to negative P external dV. Okay, we also know that for reversible work, okay, for reversible work, the external pressure is always going to be equal to that of the gas, and since we have an ideal gas, we could write our P gas as nRT over V. Okay, so upon integrating this, okay, we're treating our temperature as constant. Okay, so integrating this from the initial to the final state. Okay, so work reversible is going to be equal to negative nRT ln Vf over Vi. Okay, so it's just a matter of plugging and playing. Okay, so work, this is going to be equal to 1 mole, okay, negative 1 mole times R. So since we're solving for work over here, we want to have joules as our unit. So it's useful to use the value of R that already is in terms of joules. Okay, so 8.314 joules per mole Kelvin times the temperature, so that's 298.15 K, times Ln, the final volume. Okay, so we don't really have to convert the units for volume over here since we're just getting their ratios and the units are going to cancel out. Okay, so the overall term inside the natural logarithm expression is going to be unitless. Okay, so upon calculating this, reversible isothermal work is going to be equal to negative 2720 joules. All right. Okay, so this makes sense because the sign for work is negative, okay, and then we had an expansion process, okay? So expansion meaning that work is being done by the gas, okay? So this is going to correspond to a decrease in internal energy. Okay, so keep in mind again that for our calculations here that we've been looking primarily at work at isothermal conditions for an ideal gas. Okay, so we'll be looking at different types of work at different conditions a little later on. Okay, so before we go into those things, however, let's look at the other form of energy transfer, which is heat. Okay, so the thing that we could easily measure if ever there is heat flow is a change in temperature. Okay, so if the system is transferring heat to the surroundings, okay, so this is characterized by a negative Q, we expect that the system will be decreasing in temperature. The surroundings, on the other hand, is expected to increase in temperature. Okay? However, usually the surroundings is so large relative to the system that this change in temperature is considered to be negligible. So more or less, we usually treat the surroundings to be constant temperature despite being a heat sink or a heat source. Okay? So if the surroundings, on the other hand, is transferring heat to the system, okay, so our notation here is positive Q, we expect that the system will be increasing in energy and therefore its temperature will also increase, okay? So the surroundings, again, we're assuming that it's very, very large, so its temperature change is not going to be as significant as that for the system. Okay, so how do we determine the amount of heat transfer? Okay, so these are the major factors that determine the amount of heat transfer. Okay, so one, if there is a greater temperature change, there's usually a greater amount of heat involved, and the amount of substance and the nature of substance will also matter. Okay, so if we're looking at infinitely small heat transfers, we could combine all these factors and get this equation over here. Okay, so dq, an infinitely small heat transfer, is equal to nc dt, where c is your heat capacity, which is related to the nature of the substance, and N is your amount of substance in terms of moles. Okay, so you could also write this in terms of mass. Okay, so instead of moles, you could express the amount of substance in terms of mass instead. Okay, so you need to express your heat capacity in a different way as well. Okay, so heat capacity, this is the amount of heat required to raise the temperature of a given amount of substance by 1 Kelvin or 1 degree Celsius. Okay, so if we are writing our amount of substance in terms of mass, okay, we'll be using the specific heat capacity. Okay, so the unit is usually joules per gram Kelvin or gram degree Celsius. Okay, so we also see the specific heat capacity in terms of calorie. Okay, so molar heat capacity, this is for 1 mole of a substance, so this corresponds to this particular heat capacity over here. So again, the units is joules per mole Kelvin. Okay, so let's look at the different specific heat capacities of different materials. Okay, so the thing to keep in mind here is if ever we have a low heat capacity, okay, so let's look at different metals. So for metals, we tend to have a relatively low heat capacity over here, less than 1. Okay, so this implies that if you apply a certain amount of heat, this will be manifested in a very large temperature difference. Okay, however, if you have a larger heat capacity, so let's look at this for water over here, 4.184 joules per gram Kelvin. Okay, so that means even if you apply a certain amount of heat, okay, so this won't necessarily result in a very large temperature change. Okay, so that's why liquid water is such a good heat sink or heat source, because even though it is involved in a lot of heat flow, okay, it doesn't necessarily change its temperature drastically. So also note that heat capacity is going to be dependent on the phase of matter. Okay, so we have different heat capacities for ice, for liquid water, and for gaseous water. Okay, and it's also going to depend on temperature. Okay, so here we have water vapor at 100 degrees Celsius and it has a different heat capacity. Okay, so let's look at the dependence of heat capacity on temperature. Okay, so let's look at this graph over here. We have specific heat capacity against temperature. So we can see that there is a temperature dependence. Okay, so it tends to increase with increasing temperature. And then over here we have a divergence of two different types of heat capacities, which we'll talk about a little later. Okay, so keep in mind again that when we were writing heat flow, we're always very careful about writing it in terms of differentials. Okay, so dq is equal to nc dt. Okay, so this heat capacity over here can have a dependence on temperature. Okay, so we could rewrite this as c is equal to some function of temperature, okay? So we could write it as some constant A plus BT plus CT squared onwards, okay? So these constants over here, they're going to be unique for each different substance, and they're usually experimentally determined. Okay, so if we're going to be evaluating heat, then we need to take into account this temperature dependence of our heat capacity. Okay, so we write dq is equal to n, so let's replace our heat capacity with this expanded expression here, a plus bt plus ct squared onwards times dt. Okay, so in order to get values for heat, okay, during the entire process, okay, we need to integrate, okay, from the initial to the final states. Okay, so here we're integrating with respect to temperature, so we integrate from the initial temperature to the final temperature. Okay, so upon integrating this inexact differential, we get the absolute value of heat involved in the process. Okay, and then we have to integrate this expression here. Okay, so overall we have n times AT plus b over 2 t squared plus c over 3 t cubed onwards, okay, evaluated from the initial state to the final state. Okay, so just be very careful if ever we're given a temperature dependence of our heat capacity. Okay, so for simplicity, however, sometimes we just assume that the heat capacity is independent in the temperature range of interest. Okay, so temperature range of interest, that means the limits of our integration over here. Okay, so sometimes we just assume that C over here is a constant. Okay, so if ever we're integrating, we integrate from the initial to the final state. Okay, and then we get Q is equal to N. Okay, so instead of integrating C with respect to T, okay, we're saying that it is independent of temperature in the temperature range of interest, so we could just evaluate it as NC delta T. Okay, so this is the simplified form over here. Okay, all right, so let's also look at this special divergence over here. Okay, so we could see that at relatively higher temperatures, suddenly we have two types of heat capacities. Okay, so we have a CV and a CP. Okay, so what is that exactly? Okay, so in certain conditions, okay, so the heat that's involved in the process becomes dependent on the pathway in which that heat was transferred. Okay, so it's going to depend if the process occurs at constant temperature or at constant volume. So at constant volume, we could write the heat involved as QV. Okay, so let's just take the differential. Okay, so dQV, this is going to be equal to N. Okay, so the heat capacity is also going to be at constant volume, so NCV dt. Okay, so we could get an expression for CV. So CV is equal to 1 over N. Okay, so now we're going to get a ratio of these differentials, which gives us a derivative. Okay, so dQ over dt at constant volume. Okay, so we're just writing it in this way to indicate that it's a multivariable derivative, and then this is the variable that is kept constant, okay, our volume, right? So we could also have our heat capacity and our heat at constant pressure. Okay, so we could write dQp is equal to NCP dt. Okay, and then just solving for Cp, we get 1 over N. Okay, so partial of Q with respect to T, okay, at constant pressure. Okay, so this is the more formal definition of CV and Cp. So later on, we'll also look at other ways that we could define CV and Cp and the significance of this divergence over here. Okay, but the thing to note is that this divergence of heat capacity becomes significant only at high temperatures. Okay, so this is usually when the substance is a gas. Okay, so before this is when the substance is a liquid or a solid. Okay, so if we're going to be looking at the different values of Cp and Cv, okay, so for liquids and solids, Cp is pretty much just approximately equal to our Cv. Okay, so for gases, however, this is when the divergence becomes significant. So we could see from our plot over here that Cp is greater than Cv. Okay, so we'll look at the meaning of this exactly a little later on, okay? So for ideal gases, we could establish an exact relationship between these two values, okay? So if we get the difference between these two, Cp minus Cv, this is equal to R. Okay, so this relationship over here is going to be very useful for us in our calculations. Okay, so let's differentiate between the molecular nature of work and heat. Okay, so usually we've just been defining work and heat as different ways of energy transfer, but let's look at this molecular interpretation. Okay, so work is a force that causes a net displacement. Okay, so on a molecular basis, okay, so if we are transferring energy via work, okay, so we're applying a force and we're causing a net displacement. Okay, so there is overall an orderly molecular motion that results from the application of work. Okay, so overall we see that there is a net displacement of matter. Okay, so we can easily see this with expansion and compression processes. We could see overall the displacement of our gas, for example. Okay, so in terms of heat, however, okay, so heat is a little bit more abstract. Okay, so we just need to visualize what's happening in our molecules here. Okay, so if ever we're transferring energy via heat, what we're doing here, instead of work, which is orderly molecular motion, we're causing more disorderly molecular motion. Okay, so we could kind of see this as microscopic work. Okay, so if ever we're transferring heat to our system, we're increasing the temperature, so we're increasing the, say, the kinetic energy of our molecules. Okay, so the molecules are going to be colliding with one another. Okay, so they're causing the other molecules to move around. So you could kind of look at that as microscopic work. Okay, but since it's not really happening in any orderly fashion, okay, it's kind of chaotic. Okay, so collisions are going to be random. Okay, so that is what characterizes heat transfer. All right. Okay, so overall, let's just go over the different notations that we have for energy transfer. Okay, so if ever we have energy flowing into the system, this is characterized by a positive Q. And if ever we're having work done on the system, such as a gas compression, okay, so the sign for W is positive. Okay, so these two processes result in an increase in the internal energy of the system. Okay, so if heat is flowing out of the system, or if work is being done by the system, okay, so we have a corresponding negative Q and a negative W. So these processes would lead to a decrease in internal energy. Okay, so overall, in order to calculate the change in internal energy, we need to know these two values here. Okay, so you need to measure the amount of heat that was transferred and the amount of work that was done. Okay, so let's try to calculate this in our next example. Okay, so we have two processes over here. Let's just calculate the change in internal energy of the system during these two processes. Okay, so let's look at for A. Okay, so for A, we have a pressure volume work being done against an external pressure, and we also have an absorption of heat. Okay, so let's write down the first law. Okay, so delta U is equal to Q plus W. So we could expand our work in terms of pressure volume work. So in this case, we have a constant external pressure. So we could just write this as Q minus P delta V. Okay, so for our heat, okay, so we're absorbing heat, so that means the sign of heat is going to be positive. Okay, so positive 1000 joules going into the system. Okay, so minus, okay, the pressure volume work that's being done. Okay, so 1.5 atmospheres and the corresponding volume change. Okay, so this is 6 liters minus 4 liters. Okay, so at this point we just have to be a bit cautious about the units that are involved here. Okay, so we're calculating for a change in internal energy, so we expect this to be in terms of an energy unit. So the most convenient will be the joule. Okay, so our heat is already in terms of joule, but our work is in terms of liter atmosphere. Okay, so somehow we need to convert our liter atmosphere into joules. Okay, so you might be wondering, oh no, I have to convert all of these to SI units and whatnot, but don't worry, we already have a way that we could easily convert between these two units. Okay, so let's recall the values of R. Okay, so R has two possible values that we discussed. Okay, so we could use 0.08206 liters atmosphere per mole Kelvin, or we could write this in terms of the joule expression, so 8.314 joules per mole Kelvin. Okay, so since these two values are equal to one another, okay, so they just have different units, if you divide one value by the other, this is just dividing by a form of 1. Okay, so we could use these values as a basis to convert between the joule and the liter atmosphere. Okay, so in this particular case, we want to convert the liter atmosphere to the joule. So let's multiply this by 8.314 joule per mole Kelvin divided by 0.08206 liter atmosphere per mole Kelvin. Okay, so the liter atmosphere is going to cancel out. Okay, so the mole Kelvin also cancels out, and you're left with joules over here. Right, so we have a joule part over here minus a joule part over here. So if you calculate the delta U, the value that we should get is 696 joules. Okay, so overall we absorbed heat. Okay, and also note that we did an expansion process, right? So we went from a smaller to a larger volume at constant external pressure. So that means we're going to be losing internal energy based on this energy transfer here. Okay, so work was done by the gas. Okay, so let's try to calculate B here. Okay, so for another system, okay, so this time we have a compression, and this time we also have a release of heat. Okay, so delta U, this is equal to Q plus W. Okay, so our work is just, again, pressure volume work. Okay, so Q minus P external delta V. Okay, so our pressure is also constant here. Okay, so our Q, this time we're releasing 64 joules of heat, so that means we have a negative sign here, so negative 64 joules. Minus, okay, so note that we're going to be doing a compression here. Okay, so we expect that our overall work is going to be positive. Okay, so negative 2.50 atmospheres. Okay, so final volume is 5.5 liters. Initial volume was 8.5 liters. Okay, so don't forget to convert between liter atmosphere and joule. So 8.314 joules. Okay, so I'm just going to write it here. I'm going to be omitting the per mole Kelvin since it just cancels out anyway, over 0.08206 liter atmosphere. Okay, so liter atmosphere cancels out. Okay, so we have joule here. Okay, so if you calculate this ends up being 696 joules as well. Okay, so overall for both of these processes, this involved the same change in internal energy. Okay, so we could definitely see here that we could achieve the same change in internal energy through different pathways. Okay, so in part A, we had an expansion process and an absorption of heat, and in part B, we had a compression process and a release of heat. Okay, so just keep that in mind. Okay, so delta U, this is a state function, whereas our heat and our work, they are path functions. All right, so let's look at different processes. Okay, so for simplicity, we'll be dealing with a very simple system, namely our ideal gas system. Okay, so here are some different paths that we could investigate. Okay, so one, we have constant volume, constant pressure, constant temperature, and we'll also look at the special process here of an adiabatic process where there is no heat transfer. Okay, so a thing to keep in mind about all of these processes is that we're going to be assuming that our system is going to be a closed system. Okay, so recall again what we said about closed systems. Closed systems have a free exchange of energy, okay, with the surroundings, but it does not exchange matter. Okay, so that means we're going to be assuming that the amount of matter that we have in our system is going to be constant. All right, so for all of these processes here, we have constant amount of matter. All right, so let's look at our first process. Okay, so we'll be looking at an isochoric process or a constant volume process. Okay, so let's consider this as our first state over here. So we have volume P1, T1. Okay, so again, we have constant volume, so we could assume that this container here is going to be a rigid container. Okay, so the volume is not going to be changing. Okay, so if we say increase the temperature, okay, so we have a corresponding change in pressure. Okay, so what do we know about our ideal gas behavior? If you increase the temperature while keeping the volume and number of moles constant, we also expect that the pressure is going to increase. Okay, so you're increasing the temperature of your gas molecules over here. They have greater kinetic energy, therefore they're going to be colliding with the walls of the container more often, and therefore it's manifested as a greater pressure. Okay, so let's look at this in terms of a PV diagram. Okay, so here we have our initial state. Okay, so we have our volume, our pressure 1, temperature 1. Okay, so we're going to have constant volume, right? Okay, so if we're going to look at our next state, okay, so we're just going to be following along this line over here. Okay, so our next state, say that we go to temperature 2, okay, we have a corresponding pressure 2 over here. Okay, so it's useful to look at these pressure volume diagrams in order to get a more visual picture of what's happening in our process. Okay, so let's try to evaluate what the heat is, what the work is, and ultimately what our change in internal energy is going to be if our gas undergoes this type of process. So overall, we know that du is going to be equal to dq plus dw. Okay, so first and foremost, what can we say about the work that was being done in this process? Okay, so keep in mind that we're just going to be concerned with pressure volume work. Okay, so let's just expand these expressions over here. So du is equal to dq minus p dv. Okay, so if we're going to have pressure volume work, that means we need to have a change in volume. Okay, so in this particular case, is there a change in volume? Okay, so it's constant volume, so this implies that of course dV is 0. So if dV is 0, that means that our work here is also going to be 0. Okay, so note that we represented work as an area under the curve. Okay, so this time we don't really have an area since dV is equal to 0. Okay, so this process is very simple, so that means we don't really have any work done, so that means any heat that was transferred during this process, say that in increasing the temperature of our system, okay, so this is immediately equal to our change in internal energy. All right, so overall we could write this as du is equal to dq. Okay, so just to indicate that it's a constant volume, okay, we indicate that the heat is dqv. All right. Okay, so how did we evaluate what dqv was earlier? Okay, so we said that if heat is transferred at constant volume, you could use our heat capacity at constant volume. So dqv, this is equal to ncv dt. Okay, so upon integrating all of this, okay, so say that this is at u initial, u final, okay, so t initial, t final, okay, so overall we have delta u. This is equal to QV, which is equal to NCV delta T. Okay, so this is our value for change in internal energy and for our heat. And also just keep in mind that for an isochoric process, our work is equal to 0, right? So what's great about an isochoric process is that you could immediately correlate the heat that you measured to a change in internal energy, since we know that the work is already equal to 0. Okay, so again, any heat that is measured at constant volume is immediately equal to a change in internal energy. Right, so let's also investigate another process. Okay, so our second process is when we have an isobaric process. Okay, so meaning that we have constant pressure. Okay, so let's look at this system over here. Okay, so we have a movable piston. Okay, so we're going to be keeping our pressure constant. So our initial state is V1, P, and T1. So say that we're doing an expansion process. Okay, so we're going to be increasing V1. Okay, so we also have a corresponding increase in our temperature. Okay, so we just want to keep our pressure constant, right? So if we're increasing the volume, we're going to have a corresponding increase in temperature. Okay, so let's represent this graphically as well. Okay, so again we have the pressure being constant, right? Okay, so that means we have volume 1. Okay, this is the pressure, this is the corresponding temperature. Okay, so if we're going to be increasing the volume, okay, so that means the pressure has to remain constant, right? So we're going to be looking along this line here. Okay, so if we increase the volume, Okay, this is going to be the next state. Okay, so note again that the pressure is constant at the final and the initial states, right? Okay, so let's evaluate what's going on here exactly. Okay, so let's evaluate what the heat and the work involved in this process are and also get the change in internal energy. Okay, so again, let's start with our basic equation. du is equal to dq plus dw. Okay, so note that for all our processes, we're pretty much just starting with the same basic equation. Okay, so it's always just a matter of figuring out what the heat and the work involved in the process are. Okay, we know that there's just pressure, volume, work involved, so du is equal to dq minus pdv. Okay, so note that we have constant pressure, right? Okay, so we could also express our work over here in another way. So we're dealing with an ideal gas, right? So PV is equal to nRT. Okay, so we know that the volume is changing. Okay, so we also know that the temperature is changing. Okay, so if we write PdV, okay, so pressure is constant, right? Okay, number of moles is constant, R is a constant, okay? So a change in volume will have a corresponding change in temperature, okay? So the term PdV can be written in terms of the change in temperature times the number of moles times R instead. Okay, so we could replace this term here, PdV, with nR dt. Okay, so let's write that down. So du is equal to dq minus nr dt. Okay, so we'll clarify why we're doing this a little later on. Okay, so we also know the heat involved is at constant pressure. Okay, so we could write a little subscript over here. Okay, so dqp to indicate that this is at constant pressure. So we could write this in terms of the special heat capacity that we have for constant pressure processes. Okay, so this is going to be equal to Cp dt, and then we have this term over here, right, minus nr dt. Okay, so we have a lot of common terms here, right? So let us put them all together. Okay, so we have, okay, so let's bring together Cp minus r times n dt. Okay, so what is this value over here? Okay, so recall again that for ideal gases, okay, so for ideal gases, we know that Cp minus Cv is equal to R. Okay, so if we're solving for Cv, for example, okay, so that is going to be equal to Cp minus R. So this term over here is actually Cv, right? So that means that du is equal to NCV dt for this process over here. Alright, so let's look at the significance of this. Okay, so the change in internal energy for our process is NCV dt. Okay, so if we integrate this from the final and the initial state, this becomes delta U is equal to NCV delta T, which hopefully you note is the same thing that we got from our first process. Okay, so overall, regardless if our process occurs through isochoric or through isobaric conditions, just so long as we have the same temperature difference, we'll also have the same change in internal energy. Okay, so this is significant because, of course, our internal energy is a state function, so it doesn't matter if it went through an isobaric or an isochoric process, just so long as we have the same final and the initial states, okay, which is characterized by the change in temperature, we'll have the same change in internal energy. Alright, so this is overall our change in internal energy, so we can note that this applies for all different types of processes for an ideal gas. Okay, so our corresponding work is characterized by negative PdV, and our corresponding heat was characterized by QP or NCP dt. Alright, so this is the important thing to keep in mind. So let's go over a summary of these two processes. Okay, so let's look at the heat, the work, and overall the delta U involved. Okay, so for an isochoric process, okay, so we definitely know right off the bat that our work is going to be 0. Okay, so our heat, we could write this as QV, okay, heat at constant volume, so this is just equal to NCV delta T. Okay, so since our work is equal to 0, that means our internal energy change is directly equal to just QV. okay, which is equal to NCV delta T. All right, so again, direct measure of heat involved directly corresponds to a change in internal energy. Okay, so this is very useful. So just measuring one thing gives you the change in internal energy, okay, a state function. Okay, so this is very useful. So you could devise a way to measure heat at constant volume. So this is just through a bomb calorimeter, and you could immediately evaluate the change in internal energy. Right, so let's look at the isobaric process on the other hand. So the heat involved here is going to be QP, so you could write this as NCP delta T, and the work involved here is just going to be negative P delta V, and the change in internal energy is going to be the sum of this, but you could also write it as NCV delta T. Okay, so it's really kind of inconvenient for an isobaric process because technically you have to measure the heat and the work involved in order to evaluate what delta U is. Okay, keep in mind that in this process over here, okay, so we know that a direct measurement of heat at constant volume is directly related to change in internal energy. It's not always very convenient to measure heat at constant volume. Okay, so you need a specialized instrument in order to do that. Okay, but most heats, however, that happen in our everyday experiences are at constant pressure. Okay, so right now we're under constant atmospheric pressure. Okay, so it's more convenient to use this value here. Okay, heat at constant pressure. It'll be nice if we have a state function that is directly correlated to heat flow at constant pressure, because this stuff is easily measurable. Okay, so that's why we introduce a new state function, enthalpy. Okay, so enthalpy, this is a state function defined as the heat involved in a process at constant pressure. Okay, so enthalpy, this is directly related to QP. So let's get an expression for what enthalpy is in relation to all our other variables. Okay, so again, let's start with the first law of thermodynamics. du is equal to dq plus dw. Okay, so for a system that just has pressure volume work, okay, so we have dq minus pdv, plus if we're dealing with constant pressure, okay, so we have du is equal to dqp minus pdv. So dqp, we said that this is correlated with enthalpy, so we could write this instead as dh, okay, minus pdv. So ultimately, our expression for enthalpy, okay, dH is equal to du, the change in internal energy, plus pdv. Okay, so dqv. Okay, so also additional terms to keep in mind. Okay, so we just defined dH as dqp, right? Okay, so dqp can also be defined as ncp dt. So this gives us another definition for what Cp is. Okay, so it's correlated with this state function here. Okay, so we could write Cp as 1 over n. Okay, so let's put this in terms of partial derivatives. Okay, so dH over dt at constant pressure. Okay, so this is our alternative expression for heat capacity. Okay, so actually the same thing can also be done, so just as an additional side here. So we also said that du is equal to dqv is equal to ncv dt. Okay, so this again gives us another definition for cv. Okay, so cv can be written instead as 1 over n partial of u with respect to t at constant volume. Okay, so these are our additional definitions for heat capacities at constant pressure and constant volume. So let's just summarize our different notation here. Okay, so again, if our heat is gained by the system at constant pressure, okay, so we know that this is an endothermic process, we have a positive QP. Okay, so if, however, we have heat lost by the system at constant pressure, this is expressed as negative QP. So this is an exothermic process. Okay, so again, what's great about this is that in order to know the change in a state function, we just need to measure one thing, okay, heat at constant pressure. Okay, so again, just to emphasize, okay, so the difference between enthalpy and internal energy, okay, so again, you might be wondering, why bother with a new state function, right? We're perfectly fine with internal energy. But let's look at the definitions again. So our definition for enthalpy, okay, is just heat involved at constant pressure, okay? So keep in mind again that you can have enthalpies at non-constant pressure conditions, but overall, this is equivalent to the heat involved if the process were conducted at constant pressure conditions. Alright, so overall, we could correlate this non-state function, which is easily measurable, into a state function. Okay, so this is really convenient. Okay, so let's contrast this with internal energy. Okay, so for internal energy, we needed to know the heat and the work involved. Okay, so that means we need to measure these two parameters in order to arrive at delta U. Okay, so it's more convenient to measure just one thing in convenient conditions. Okay, this is constant pressure. So right now, our conditions are usually at constant pressure. Okay, so we can easily measure enthalpy changes. Okay, so this is the importance of our enthalpy. So later on, we'll see that most of the measurements that we have are in terms of enthalpy instead. Okay, so another interesting question to address is why Cp is greater than Cv. Okay, so now that we're familiar with the different processes in which these terms are involved in, okay, we could investigate why this condition is true. So let's consider different processes that occur at constant volume versus constant pressure. Okay, so if we have a constant volume process, that means there's no work, right? So this is an isobaric process, no work. So that means if we're inputting a certain amount of heat, okay, so all that heat is just going to go to increase the temperature of our system. Okay, so that means we just need a little bit of heat in order to increase the temperature by a certain amount. All right, so if, however, we're looking at a constant pressure process, okay, so the inputted energy can go to increase both the temperature and to do expansion work. Okay, so that means this amount of heat, so say that the amount of heat involved in these two processes are the same, not all of it is going to increase the temperature, but some of it is going to do some expansion work. Okay, so that means just a part of this heat is going to go to increase the temperature. So that means if you want to have equivalent temperature changes in these two processes over here, you need to input more heat in order to increase the temperature by the same amount. So what is the heat capacity involved here? The heat capacity involved is your Cp. Okay, so that means your heat capacity at constant pressure is expected to be larger because some of that heat goes into expansion process rather than temperature increase. All right, so hopefully it's clear as to why Cp is greater than Cv. All right. Okay, so let's look at the Cp and Cp values for ideal monatomic and diatomic gases. Okay, so as discussed earlier, we know that for an ideal gas, okay, so all of the internal energy is typically just a sum of kinetic energy plus potential energy, right? However, for an ideal gas, our potential energy is just zero. So that means the internal energy is just equal to kinetic energy. Okay, so recall again our discussion from our kinetic molecular theory. We said that our internal energy is equal to 3/2 nRT. Okay, so if we're looking at changes in internal energy, it's just going to be dependent on changes in temperature. So delta U is going to be equal to 3/2 nR delta T. Okay, so we also have another expression for delta U, right? We said that delta U is also equal to NCV delta T. Okay, so a bunch of things could cancel out here. So N cancels out, delta T cancels out. So ultimately we have an expression for CV. Okay, so CV is equal to 3/2 R. Okay, so this is for a specific case. Okay, so this is for a monatomic ideal gas. Okay, so why monatomic? So monatomic gases are just perfectly spherical, right? Okay, so that means their kinetic energy is wholly translational. Okay, it's going to be different once we start dealing with diatomic gases. Okay, so Cp is going to be, recall again the relationship Cp minus Cv is equal to R, right? So that means that Cp is going to be Cv plus R. Okay, so we just add an additional R to this value over here of Cv. So Cp is going to be 5/2 R, right? So these are important values to remember once we're dealing with a monatomic ideal gas. Okay, so we could also look at the value for a diatomic gas. Okay, so a diatomic gas is going to look this way. Okay, so you have two atoms together. Okay, so previously for a monatomic gas, we said that this just has translational motion. Okay, so once we start dealing with a diatomic gas, you have additional rotational motion. Okay, so the effect of this additional type of motion increases our heat capacity. Okay, so specifically, Cv becomes 5/2 R, okay, and then Cp becomes 7/2 R. Okay, so it's very simple to just deal with these two types, monatomic and diatomic, because we could take into account the different types of motion, kinetic energy motion that's involved. Okay, however, once we start dealing with more complicated gases, okay, so polyatomic gases, whereas the kinetic energy goes becomes a little bit more complicated because you start having more complicated molecular motions. Okay, so keep in mind that for a diatomic ideal gas, okay, the Cv is going to be 5/2 R and the Cp is going to be 7/2 R. All right. Okay, so again, for more complicated gases, usually we have to experimentally determine what the Cp's and the Cv's are. Okay, so let's look at another process, an isothermal process. Okay, so actually we discussed this process in detail earlier, especially in terms of its work. Okay, so we have reversible isothermal work and reversible isothermal work. Okay, so now let's just look at our values for delta U, delta H, and Q. Okay, let's write down our expression for delta U. Okay, so we know that delta U is just NCV delta T. Okay, so delta H is also going to be NCP delta T. Okay, so these two equations are going to hold true for all ideal gas processes. Okay, however, let's note what's happening here. Okay, so delta T. Okay, so we have an isothermal process, right? So this implies that delta T is going to be 0. Okay, so this in turn implies that a change in internal energy is also going to be 0. And the change in enthalpy is going to be 0 as well. Okay, so overall, if we have an ideal gas process at isothermal conditions, the change in internal energy and the change in enthalpy is expected to be 0. However, this doesn't mean that the heat and work involved are going to be 0 as well. Okay, so we know that delta U is equal to Q plus W. So since delta U is equal to 0, this implies that any heat flow is just going to be equal in magnitude but opposite sign to our work. Okay, so this implies that if our system does work, the work has to come from the internal energy, right? However, we have a net change of 0 for our internal energy. So that means that the work that was done by the system during the expansion process should have come from an absorption of heat. All right. Okay, so that means that the system should have absorbed an equal amount of heat in order to do that work. Okay, so let's just summarize this. Okay, so if we're dealing with an irreversible work, our work irreversible is going to be equal to negative P external delta V, as we discussed earlier. So this implies that our heat, okay, so let's just note that it's irreversible, just to note what this is. This is going to be the negative of our irreversible work, or it's just going to be positive P external delta V. Okay, so let's also look at reversible work. So we discussed what this equation is. Okay, so this is going to be negative nRT ln V2 over V1. Okay, so this is for our reversible work. So this implies that our reversible heat is just going to be the positive of this. Okay, so this is going to be positive nRT ln V2 over V1. All right. Okay, so this is for our isothermal process. Okay, so Just note that any work done by the system is going to be due to any heat input for the system. Okay, so let's try to solve for this problem over here. Okay, so we have a 4-liter sample of hydrogen gas at 15 atmospheres and 25 degrees Celsius, and it's allowed to expand to a final pressure of 1 atmosphere. So we just want to calculate the different parameters if the gas expands isothermally and reversibly, or isothermally and irreversibly. So the first step in this problem is to figure out the different states. Okay, so initial state, final state. Okay, so let's consider the initial state. We have pressure, volume, temperature. Okay, so we also want to figure out the number of moles as well, because this will be important in our calculations. Okay, so the initial pressure is equal to 15 atmospheres. Okay, initial volume is 4 liters. Temperature is equal to 25 degrees Celsius, so let's just put that in terms of Kelvin. Okay, and the number of moles, we could calculate that based on our data over here. So we just need to use the ideal gas equation. So N is equal to PV over RT. So plugging in these values over here, we should get 2.45 moles. Okay, since we're dealing with an isothermal process and it's a closed system, these things are going to be constant at the final state. Okay, so our final temperature is also going to be 298.15 K, and the number of moles is going to remain constant. Okay, so the final pressure, okay, it's indicated over here, so this is going to be 1 atmosphere. So we could also calculate the final volume. Okay, so actually we could just use, since our number of moles and temperature is constant, we could just use Boyle's law. Okay, so we have PI VI is equal to PF VF. Okay, so calculating for VF, this is just PI VI over PF, and then the value that you should get is around 60 liters. Okay, so we'll be expanding our gas to 60 liters. Okay, so let's try calculating this irreversibly first. Okay, so we know for both cases, so since we have an isothermal process, delta U is equal to delta H, which is just equal to 0. Okay, so it's just a matter of calculating the work involved. Okay, so reversible work for an ideal gas at isothermal conditions is equal to negative nRT ln VF over VI. Okay, so this is equal to, okay, so we have 2.45 moles of gas times R, so 8.314 joules per mole Kelvin, and our temperature, which is 298.15 Kelvin, times the ln, so let's just continue down here, ln of our volumes. Okay, so we have 60 liters over 4 liters. Okay, so our reversible work, this should be equal to negative 60,400 joules. Alright, so this makes sense since we have an expansion process, so the work involved is negative. Okay, so this also means that the reversible heat involved in the process is equal in magnitude but opposite in sign. So this just means that the Q is positive 16,400 joules. Okay, so overall the meaning of this, in order to do your reversible expansion, is that your system had to absorb this amount of heat in order to do this amount of work, because the overall change in internal energy was equal to 0. Right? So this is for reversible work. So now let's calculate this if this process occurred irreversibly. Okay, so we'll still be dealing with the same final state. Okay, so let's just recall again that in this plot, okay, so we have our PV curve over here, so pressure, volume. Okay, so if we have, this is our 4 liters, and this is our 60 liters, right? So for reversible work, we took into account the entire area under this PV curve at 25 degrees Celsius. However, if we're looking at irreversible work, okay, so our final pressure is going to be equal to the external pressure, okay? So P external, this is equal to the final pressure, so this is going to be 1 atmosphere. So that means we're just going to be concerned with this part over here for our irreversible process. Okay, so let's just calculate that really quickly. All right, so for part 2, Okay, so again, we know that delta H is equal to delta U, which is equal to 0. Okay, so an isothermal process. And we also know that work irreversible, this is equal to negative P external delta V. Okay, so our external pressure, this is 1 atmosphere, right? And our change in volume, our final volume was 60 liters, and our initial volume was 4 liters. Okay, so again, let's just convert this to joules. Okay, so we'll use our conversion here. 8.314 joules per 0.08206 liter atmosphere. Okay, so if we calculate this, the irreversible work done by the system will be negative 5,670 joules. Okay, so just as a double check, the magnitude of work done by the system, if it's done irreversibly, is much less than that if it were done reversibly. Okay, so this is our irreversible work. So for our heat involved, so this is going to be an equal magnitude but opposite signs. So this is going to be positive 5,670 joules. Right? So this is how we calculate the parameters involved for an isothermal process, okay, if it were reversible or irreversible. Right, so the next thing that we'll be looking at is a special process, okay? So we'll be looking at a so-called adiabatic process, okay? So we could have an expansion or contraction occurring in adiabatic conditions, but for our investigations, we'll consider an expansion. But keep in mind that the same conclusions that we get here are going to apply for compression processes, okay? So what do we mean by an adiabatic process? This means that our system is isolated. So that means we have no heat flow, okay? So if ever we have an initial state here, okay, so we're going to have volume 1, pressure 1, temperature 1, okay? During an adiabatic process, all of these parameters are going to change in the final state. Okay, so what's tricky about adiabatic processes then is that we don't have any parameter that is constant. Okay, so all of these values here are going to change. Okay, however, what we do know about an adiabatic process is this over here. Okay, so let's investigate this. Let's look at the first law of thermodynamics. du is equal to dq plus dw, right? So we know that there's no heat flow, so this time we know that dq, this is going to be equal to 0. Okay, so ultimately du is going to be equal to just the work involved. Okay, so there's no heat flow, so that means any energy exchange that the system is going to do is just going to be through work. Okay, so in our particular example, we're doing an expansion process, right? So that means that the work over here, okay, this is going to be negative. Okay, so if our gas is expanding adiabatically, okay, that means the system is doing work, right? So where is the energy going to come from to do work? It's going to come from the internal energy, okay? So that means if our system is doing work, that means immediately right off the bat we know that there's going to be a decrease in our internal energy, okay? So it's not going to be offset by any absorption of heat because dq is already equal to 0 in our system over here. Okay, so what do we know about this system over here? We know that since we have an expansion process, okay, so let's expand these terms over here. This is NCV dt, and this is negative P dV. Okay, so for an expansion process, this whole term over here is going to be negative. Okay, so this also implies that since this is positive, dt is going to be negative as well. Okay, so during expansion process, we're always going to see a decrease in temperature. Okay, so this makes sense because the energy used to expand the gas comes from the internal energy. Okay, so it's not going to be offset by any absorption of heat from the surroundings. Okay, so let's look at this in terms of a pressure volume diagram. Okay, so here we have our initial pressure and our initial volume, initial temperature. Okay, so if we're expanding our gas from volume 1 to volume 2, okay, so we need to draw another isotherm. Okay, so we said again that if we are expanding, our temperature is going to decrease afterwards. Okay, so that means that temperature 1 is going to be greater than temperature 2. Okay, so the isotherm that we're going to draw here next is going to be at a lower temperature than temperature 1. Okay, so overall, we need to have this isotherm here, T2. Okay, so if we're going to expand to volume 2, okay, so let's look at the corresponding pressure at which we have volume 2 and temperature 2. Okay, so here we have our new state here. Okay, so again, note that all the temperature, volume, and pressure values are going to be changing after the process. Okay, so we could have two types of adiabatic expansions. Okay, so we could have it done reversibly or irreversibly. So let's look at the reversible process. Okay, so recall again for reversible processes that the external pressure is constantly going to adjust to the pressure of the gas, okay? So in contrast to reversible isothermal, however, okay, we won't exactly just consider the area under the curve over here, okay? So if we actually draw out the process, okay, the process looks like this here, okay? So the pressure is constantly going to adjust in this fashion over here. So the corresponding work will not be an area under an isotherm, but rather the area under this part over here, okay? So the corresponding work is this blue shaded region here. Okay, so it's kind of difficult to evaluate what this is exactly. So we could use the equations that we know for an adiabatic process in order to evaluate what our work is, okay? So for one, we don't really actually need to know what this curve is over here, okay? We could just correlate the work with the change in internal energy. So in general, we know that du is equal to dq plus dw, right? So for an adiabatic process, dq is 0, so that means du is just equal to dw, okay? So in order to evaluate work, we just need to calculate the change in internal energy. Okay, so we could expand this expression as NCV dt, okay? So in order to calculate work, we could just calculate NCV dt. The tricky part is knowing the final state over here, okay? So we need to be able to calculate the final state in order to know the change in temperature over here, okay? So we'll be using this relationship of du is equal to dw in order to establish a relationship between the final temperatures and the final volumes, okay? So we could expand dw in terms of our pressure volume work, okay? So negative P external dV, but since we're doing this reversibly, we know that our external pressure is equal to pressure of our gas, okay? So we could also express the pressure of our gas in terms of temperature and volume, okay? So using the ideal gas equation, we could write P gas as nRT over V, okay? So now we have negative nRT over V times dV, which is equal to NCV dt, okay? So we have a bunch of differentials over here. So we have this differential equation. So before we start integrating, we need to make sure that all the variables are in the right place. Okay, so let's do a bit of rearrangement, and we could also cancel out the number of moles over here. So let's bring all the temperature terms on the left side and all the volume terms on the other side. Okay, so let's rewrite this as dt over t is equal to negative r over cv times dv over v. Okay, so let's also introduce another term with respect to this value over here. Okay, so we know that r is equal to cp minus cv. Okay, so if we get the ratio, okay, so if we divide r by cv, okay, so let's divide this over here. Okay, so we get cp over cv minus 1. Okay, so the ratio of cp over cv, this is sometimes just designated as a new symbol. Okay, so we could designate this as gamma. Okay, so gamma minus 1, this is r over cv. Okay, so we could replace this term here, the ratio of r over cv, with gamma minus 1. Okay, so dt over t is equal to negative gamma minus 1 dv over v. Okay, so now let's integrate this expression over here. Okay, so let's move on to the next slide. Okay, so let's rewrite this here. So dt over t is equal to negative gamma minus 1 dv over v. Okay, so let's integrate. So assuming that our heat capacities are constant and independent of temperature, okay, so we can integrate this with respect to the initial temperature, the final temperature, okay, and then we could also integrate this with respect to the initial volume and the final volume, okay. So if we integrate this, we should get the natural logarithm, okay, so ln t2 over t1 is equal to negative gamma minus 1 ln V2 over V1. Okay, so we could also do additional rearrangements. Let's bring in this term here, this coefficient, as an exponent of the term inside the natural logarithm. Okay, so we get ln T2 over T1 is equal to ln V2 over V1, all raised to negative gamma minus 1. Okay, so note that we have these two terms with a natural logarithm, so ultimately we could just get the exponential of the entire expression in order to get rid of this ln. Okay, so after that we could get T2 over T1, okay, is equal to V2 over V1 raised to negative gamma minus 1. Okay, so this is the relationship between the final and initial volumes and temperatures. Okay, so usually we're given the initial state, so temperature 1, volume 1, and we're also given one parameter of our final state, such as volume. Okay, so we could use this relationship in order to calculate for temperature. Okay, so there's many other ways that we could derive alternative expressions for this relationship over here. Okay, so in this case, we're given volume and temperature, but sometimes we're given just temperature and pressure, for example. Okay, so an alternate but equivalent expression for this would be T2 over T1 is equal to P2 over P1. Okay, and then we'll be raising this to gamma minus 1 over gamma. Okay, another way is through pressure and volume. Okay, so if you want to know the pressure and volumes, okay, we could relate this in the following way. So we could be written as P2 V2 raised to gamma is equal to P1 V1 raised to gamma. Okay, so all of these expressions over here can be derived from this basic expression. Okay, so we just need to replace the variables using the ideal gas equation. Okay, so I'll leave that derivation up to you guys, right? Okay, so overall we have an expression that would allow us to calculate the final temperature of our system. So in order to solve for work, okay, so we could just write du is equal to dw. So this is equal to ncv dt. Okay, so we could just evaluate these. So initial and final states. Okay, so initial and final temperatures. Okay, so delta U is just equal to our work, okay, which is equal to NCV delta T. Okay, so delta T is what we could solve using that equation that we just derived earlier. All right, so this is for your reversible adiabatic process. Okay, so this again, the same principle can hold for a compression process. All right, so now let's look at if we could do this process irreversibly. Okay, so if we're going to do this irreversibly, that means we have a constant external pressure that is exerted. Okay, so recall again what we said about constant external pressure, okay, and irreversible processes. That means that the external pressure of our system should have been equal to the final pressure of our system after the expansion. Okay, so this should be equal to our P external. Okay, so if we're looking for the work involved in this process, that means it's just going to be this region over here. Okay, so the basic relationship of dW is equal to negative P external dV is going to hold. Okay, so in this case we have a constant external pressure, okay, and then we have the corresponding change in volume. Okay, so again, this issue is still here. Okay, so we don't really know exactly what this final state is going to be. Okay, so we don't know what the temperature change is going to be and whatnot. Okay, so we need to be able to calculate that. Okay, so again, we could use the same relationship that we had earlier for our reversible adiabatic process. Okay, so the relationship of du is equal to dw still holds. Okay, so it's an adiabatic process, so dq is equal to 0. Okay, so we could make the corresponding replacements. Okay, so ncv dt still holds, and we also have negative P external dV as our irreversible work. Okay, so recall again what we're doing here, guys, is that if we're doing irreversible work, okay, so where does the energy come from in order to do that irreversible work? It comes from the internal energy. Okay, so that means we're going to have a corresponding change in our internal energy based on the work that we did. Okay, So let's try to calculate this. Okay, so we could directly integrate these expressions here. Okay, so we have it from T1 to T2. Okay, V1 and V2. Okay, so again, our goal is to solve for the final state. Okay, because we don't really know where it's going to end up expanding to as we have no heat flow. Okay, so upon integrating this, we should get NCV. Okay, so T2 minus T1. Okay, and then this over here, keep in mind that this is going to be a constant. Okay, so we could just write this as negative P external V2 minus V1. All right. Okay, so let's expand based on this. Okay, so let's go to a fresh slide over here. All right, so let's rewrite this. So we have NCV T2 minus T1 is equal to negative P external V2 minus V1. Okay, so we can expand these volume expressions in terms of pressure and temperature instead. Okay, so from the ideal gas equation, we could write volume as nRT over P. Okay, so note that the variables that we have here are temperature and P. Okay, so we could also replace our P external with one of the pressures of our gas. Okay, so recall again that this pressure 2, okay, so based on our principles of mechanical equilibrium, this should be equal to our external pressure. Okay, so we could write this as negative P2 times, okay, so for V2 we have nRT2 over P2 minus nRT1 over P1. Okay, so this is going to be equal to NCV T2 minus T1. Okay, so we could see that there are some things that could cancel out. So number of moles could cancel out. Okay, and then we could also distribute pressure 2 over here. Okay, and then we should get CV times T2 minus T1 is equal to negative RT2 plus P2 RT1 over P1. Okay, so the equation looks really messy right now, so let's try to simplify this a little bit. Okay, so let's rewrite our equation. So we have CV over R, T2 minus T1 is equal to P2 over P1, T1 minus T2, right? Okay, so let's just rearrange some of this and also do some distribution. Okay, so we have CV over R T2 minus CV over R T1 is equal to P2 over P1 T1 minus T2. Okay, so let's transfer each of these terms. Okay, so let's bring all the terms that contain T2 on one side and all the terms that contain T1 on the other side. Okay, so we have CV over R T2 plus T2 is equal to P2 over P1 T1 plus CV over R T1. Okay, so let's factor out the temperature terms and we will get T2 CV over R plus 1 is equal to T1, okay, CV over R plus P2 over P1, okay, the pressure ratios. Okay, so let's do additional rearrangements. Okay, so we could get the ratio of the temperatures. So T2 over T1 is equal to, okay, so we have CV over R plus P2 over P1 divided by CV over R plus 1. Okay, so here we have our equation that relates the temperatures, the initial and the final temperatures, with the initial and the final or the external pressure during an irreversible adiabatic process. Okay, so again, guys, the key to this is to figure out what the final state is in order to calculate the change in internal energy and the work. Okay, so let's try to apply all of these equations, and we can also emphasize important things about adiabatic processes using this particular problem over here. Okay, so in this problem, we have a 4-liter sample of hydrogen gas, okay, at 15 atmospheres and 25 degrees Celsius. Okay, so actually this problem here is the same as what we used earlier for our isothermal process. Okay, so let's write down first our initial state. Okay, so we already know the volume, so this is 4 liters. We know the pressure, this is 15 atmospheres. The temperature is 298.15 Kelvin, and earlier we solved for the number of moles, which was 2.45 moles. Okay, so now let's look at the final state. Okay, so note that the only thing that we really know about the final state is the final pressure. Okay, so the final pressure is going to be 1 atmosphere. So always keep in mind that we have a closed system, so the number of moles is always going to be constant. And we do not know, however, what the final temperature and the final volume is going to be. Okay, but we need to know what the final temperature is going to be in order to calculate for the corresponding work, change in internal energy, and the change in enthalpy. Okay, so right off the bat, we already know that Q is going to be 0 since we're dealing with an adiabatic process. Okay, so in order to calculate for U and work, we need to have NCV delta T, right? Okay, so we could use the equation that we derived for a reversible process, okay, but note that in this particular example, we're given the initial and the final pressures, and we're given the initial temperature, and we're really interested in figuring out what the final temperature is going to be. Okay, so for the equation that we derived, we had a relationship between the final initial temperatures and the final initial volumes. Okay, however, we could derive an equivalent expression from this, okay, using instead pressures. Okay, so T2 over T1, this will be equal to P2 over P1 raised to gamma minus 1 over gamma. Okay, so we know the final and the initial pressures, and we also know the initial temperature, and we also know what these expressions should be equal to. Okay, so we're dealing with H2 gas. Okay, so H2 gas, this is a diatomic gas, so that means Cp, this is going to be equal to 7/2 R, and Cv, this is going to be equal to 5/2 R. Okay, so if we're calculating for gamma, gamma is the ratio of Cp and Cv, so we divide these two things together, we should get 7/5. Okay, so let's solve for T2 using this equation over here. So T2, this is going to be equal to, okay, so pressure 2, that is 1 atmosphere. Okay, so we also have 15 atmospheres, all raised to gamma minus 1, so that is 7/5 minus 1 over 7/5 times temperature 1. Okay, so temperature 1 is 298.15 Kelvin. Okay, so solving for temperature 2, we get 137.5 Kelvin. Alright, okay, so note that this makes sense, right? Because we're doing an expansion process. Okay, so we know that our work is expected to be negative, so therefore we expect a decrease in temperature because the energy to do the work comes at the expense of the internal energy. Okay, so now that we know our final temperature, let's calculate for our state functions and our work. Okay, so overall we know that Q is equal to 0, right? So delta U, which is equal to our work as well, is going to be NCV delta T. Okay, so we have 2.45 moles of our gas. Okay, our CV, this is going to be equal to 5/2 R, or 8.314 joules per mole Kelvin. And our change in temperature, so our change in temperature is 137.5 Kelvin, which is our final temperature, and our initial temperature is 298.15 Kelvin. Okay, so our delta U and our work, this is going to be equal to negative 8,180 joules. Okay, so this makes sense. Okay, so we have a corresponding decrease in internal energy because our system did work against the surroundings during its expansion process. Okay, so delta H on the other hand, this is going to be equal to NCP delta T. Okay, so we can just plug in all the values that we know, 2.45 moles of gas. Okay, so Cp is equal to 7/2 R. Okay, so 8.314 joules per mole Kelvin, and we have the same corresponding change in temperature. Okay, so enthalpy, this is going to be equal to negative 11,500 joules. Okay, so there we have it. So we have Q, okay, which is equal to 0. We have delta U and work, which is equal to negative 8,180 joules, and enthalpy, which is equal to 11,500 joules. Okay, so this is if the process occurred reversibly and adiabatically. Okay, so now let's solve for the next process over here. So let's try to see what happens if the process occurs irreversibly. Okay, so what do we know about an irreversible process and a reversible process? Okay, so if we're doing an expansion, we know that for a reversible process, the work done by the gas is going to be the maximum work. Okay, however, if we do this irreversibly, we know that our gas is going to do less work. Okay, so we expect that the work that we're going to be solving for is going to be less than this value over here. And we also expect that since our gas is going to do less work if it did it irreversibly, that the change in temperature is going to be smaller. Okay, so less work means that our system needed to decrease the internal energy by a smaller amount, which is manifested in a smaller change in temperature. Okay, so we need to use a different equation in order to solve for this. So again, we have the same initial state. Okay, so again, let's write down our initial conditions. Okay, so our volume is 4 liters, our pressure is 15 atmospheres, our temperature is 298.15 Kelvin, number of moles is still 2.45 moles, and our final state, okay, so it only knows something about the pressure, okay, so that is 1 atmosphere. Okay, so we don't know the volume or the temperature. Okay, so again, closed system, so same number of moles before and after. Okay, so we could use our equation that we just derived earlier in order to solve for the final temperature. Okay, so our equation was, okay, so we had T2 over T1 is equal to CV over R plus the ratio of our pressures over CV over R plus 1. Okay, so we know what CV is. This is going to be equal to 5/2 R. Okay, so let's solve for temperature 2. Okay, so temperature 2, this is going to be 5/2 R divided by R. So this cancels. Okay, so plus pressure 2, which is 1 atmosphere divided by 15 atmospheres divided by, okay, 5/2 R over R, okay, cancels again, plus 1, times our initial temperature, which is 298.15 Kelvin. Okay, so solving for this, we have 219 Kelvin as our final temperature. Okay, so again, note that the drop in temperature is not as drastic as it was for our adiabatic reversible process, because we expect that the gas, if it did the work irreversibly, that we have less work done. All right? Okay, so now let's use this final temperature in order to calculate for the values of work, change in internal energy, and change in enthalpy. Right off the bat, we know that Q is equal to 0. Okay, so delta U, this is going to be equal to work. So this is equal to NCV delta T. So this is 2.45 moles again, times CV, which is 5/2 R, or 8.314 joules per mole Kelvin. And our change in temperature, this is going to be 219 Kelvin minus 298.15 Kelvin. So our corresponding delta U and work, this is going to be equal to just negative 4,030 joules. Okay, so change in enthalpy, on the other hand, this is again same basic equation, NCP delta T. So this is 2.45 moles times 7 over 2, 8.314 joules per mole Kelvin, and our corresponding change in temperature, 219 minus 298.15 Kelvin. Okay, so our change in enthalpy is expected to be negative 5,640 joules. Okay, so our prediction is correct. Okay, so we ended up doing less work if we did the process irreversibly. So we also have a corresponding smaller decrease in internal energy. All right, so this is how we calculate changes if our process is an adiabatic process. Okay, so note again, the tricky part for this is to calculate the final state, okay, particularly the final temperature. All right, so let's summarize the different ideal gas processes that we just discussed. Okay, so we talked about isochoric, isobaric, isothermal, and an adiabatic process. Okay, so for an isochoric process, right off the bat, we could say that our work is equal to 0. Okay, so for heat, we could say that heat occurs at constant volume. So this is going to be equal to NCV delta T. Okay, so for change in internal energy, okay, so we know that we could define change in internal energy for an ideal gas always as just NCV delta T. Okay, so for Enthalpy, on the other hand, we could say that this is NCP delta T. Okay, so keep in mind that if ever we have our heat at constant volume, this is directly related to our change in internal energy. Okay, so for an isobaric process case, we still have the same relationships for delta U and delta H. Okay, so this is going to be NCV delta T, and this is still going to be equal to NCP delta T. Okay, so again, delta U and delta H, they are state functions, so it doesn't really matter how you reach your final state. Okay, so for heat, okay, so this is going to be equal to QP, which is equal to NCP delta T. So any heat that you measure is going to be equivalent to your change in enthalpy. Work, on the other hand, you could just easily write this as negative P external, so you have a constant pressure times the change in volume. Alright, so for isothermal processes, on the other hand, okay, so we still have the same relationships for delta U and delta H. This is still NCV delta T, this is still NCP delta T, but since we still have isothermal conditions, delta T and delta T here are going to be 0, so therefore overall, delta U is going to be 0, delta H is going to be 0. Okay, so again, be very careful. Okay, so this is only true for ideal gas processes. Okay, so delta U is going to be 0 if we have an isothermal ideal gas process. Okay, so this is not going to hold true for other cases such as phase changes. Okay, so phase changes occur at isothermal conditions, right? So that does not mean that the enthalpy or the change in internal energy are going to be 0, because of course we won't be dealing with an ideal gas if we have a phase change. Okay, so since our delta U is equal to 0, this means that our work and our heat are going to be equal in magnitude but opposite sign. Okay, so it's just going to depend on if we do the process reversibly or irreversibly. Okay, so if we have reversible work that's done, this is going to be equal to negative nRT ln V2 over V1. Okay, so again, our heat is going to be in equal but opposite sign to our work. So if we have reversible work that's being done, our heat is going to be positive nRT ln V2 over V1. Okay, so again, any heat flow that goes into the system immediately goes into work. Okay, so this is to ensure that delta U is going to be equal to 0. Okay, so for irreversible work, we could just write this as negative P external delta V. Okay, so this means that the heat, if irreversible work was done, is going to be equal to positive P external delta V. So for an adiabatic process, on the other hand, Q immediately you can say is going to be equal to 0. Okay, so that means that our work is just going to be equal to delta U. Okay, so delta U, it still has the same relationship, so it's still going to be expressed as NCV delta T. Okay, our delta H is also going to be expressed as NCP delta T. Okay, so the tricky part again for adiabatic processes is to determine our final temperature. Okay, so how do we determine final temperature? This is going to depend if the process occurs reversibly or irreversibly. Okay, so we could use the equations that we just derived earlier in order to calculate for the final temperature, which will allow us to calculate NCV delta T and correspondingly calculate for our work. Okay, so these are the different processes that an ideal gas can undergo. Okay, so note again that for state functions, we still have the same basic equation. Okay, so for delta U, it's still NCV delta T. For delta H, it's still just NCP delta T. Okay, so it's just going to change for our non-state functions. Okay, so again, our non-state functions are going to be dependent on the pathway in which we achieve our final state. Okay, so let's try to apply all of the things that we know about the different ideal gas processes in order to solve for this particular problem. Okay, so in this particular problem, we're dealing with 1 mole of an ideal diatomic gas which undergoes the following cyclic reversible process. Okay, so we go from point A to B to C, and finally back to A. Okay, so we want to calculate the heat, the work, the change in internal energy, and the enthalpy for each step of the process and for the total cycle. Okay, so first and foremost, we need to define the states at each of these points here. Okay, so what we're given only is that we have our different pressures here, and we're also given this isotherm that is at 200 Kelvin. Okay, so note, however, that point A and point C are along this isotherm. Okay, so let's define each of the states at the different points. Okay, so we want to figure out the pressure, the volume, and the temperature. Okay, so right off the bat, we know that the pressure at point A is going to be 4 atmospheres. Okay, so the volume isn't that obvious yet, but we do know that the temperature is 200 K. Okay, so the volume can easily be solved just using the ideal gas equation. So volume is just nRT over P. So we know that there's 1 mole, we know the temperature, we know the pressure. So solving for this, we should get 4.103 liters. Okay, so let's just write this down. The volume over here, this is 4.103 liters. Okay, so for point B on the other hand, so let's try to solve for the pressure, the volume, and the temperature here. So the pressure is immediate because we know that point B is along this pressure over here, so we have 4 atmospheres. However, we don't really know what the temperature is, nor we know what the volume is. Okay, so for point C, however, the volume might be solvable because we know that point C is along the temperature 200 K isotherm. Okay, so the pressure at point C is 1 atmosphere, the temperature is 200 K, so we can solve for the volume here. Okay, so using nRT over P, our volume is going to be 16.412 liters. Okay, so the volume at this point here is 16.412 liters, and we know that point B is along this same isochore or constant volume line. Okay, so the volume at point B is going to be 16.412 liters. Okay, so this allows us to calculate the temperature this time. So the temperature is just going to be PV over NR. So solving for the temperature, we know that this is going to be 800 K. Alright, so now we know all of the different states for each of the points. So this will allow us to calculate the heat, the work, and the changes in internal energy and enthalpy for each of the steps. Okay, so for step 1, this is A to B. So this is at constant pressure, right? So this is an isobaric process. Okay, so step 2, this is point B to C, so this is at constant volume, so this is our isochoric process. And for step 3, this is from C to A, so this is our isothermal process. Okay, so after calculating each of the steps, we could finally calculate for the overall process. Okay, let's try to calculate each step of the way first. Okay, let's solve for our first step. Okay, so for step 1, this is A to B, right? So this is our isobaric process. Okay, so let's solve for QP, which is going to be equal to delta H. So this is just equal to NCP delta T. Okay, so we know that our gas is a diatomic gas, so we know values for CP and CV. Okay, so CP, this is going to be equal to 7/2 R, and our CV, this is going to be equal to 5/2 R. Okay, so calculating for this, we know that we have 1 mole. Okay, our CP is equal to 7/2 R, so the value of R that we should use is 8.314 joules per mole Kelvin, and our change in temperature is 800 minus 200 Kelvin. Okay, so upon calculating this, we will get 17459 joules. Okay, so this is the change in enthalpy and the corresponding heat. Okay, so let's also calculate delta U. Okay, so delta U, this is going to be equal to NCV delta T. Okay, so same plug in, so 1 mole. Okay, so CV is equal to 5/2 R, and our change in temperature is 800 minus 200 Kelvin. Okay, so the corresponding delta U that we should get is equal to 12471 joules. Okay, so we can calculate work in 2 ways, but the direct way is just to calculate negative P external delta V. So this is going to be negative 4 atmospheres times the change in volume, so that is 16.412 liters minus 4.103 liters. So note that currently we have liters atmosphere, so we need to convert this to joules. So this is 8.314 joules per 0.08206 liter atmospheres. Okay, so upon calculating this, our work is going to be equal to negative 4988 joules. Okay, so a very useful way to double check our work at this point is to double check if the first law of thermodynamics holds. Okay, so delta U is equal to Q plus W, right? So that means if we sum up the heat involved, which is 17,459 joules, and the work involved, which is negative 4988 joules, we should get our change in internal energy as calculated. So if we sum this together, okay, so if we sum this and this, we actually do get 12,471 joules. Okay, so you could try that out with your calculators right now. So this works out. Okay, so we're good to go. Okay, so now let's try to solve for our next step. Okay, which is our isochoric step. Okay, so step 2, this is from point B to C. Okay, so right off the bat, we know that our work is going to be equal to 0 because we have no volume change. Okay, so next we can calculate for QV, which is going to be directly equal to our change in internal energy. Okay, so this is just going to be equal to NCV delta T. Okay, so calculating for this, we have 1 mole again, and then we have 5 halves R, and our change in internal energy, our final temperature is going to be 200 K, so 200 minus 800 K. Okay, so this is going to be equal to negative 12,471 joules. Okay, so let's also look at delta H. So delta H, this is going to be NCP delta T. So this is just again 1 mole. Okay, CP is 7 halves R, and our change in temperature is 200 minus 800 K. So this is just going to be equal to negative 17,459 joules. All right, so these are our values for our isochoric process. Let's move on to our isothermal process. Okay, so our isothermal process is going to be a reversible one. Okay, so let's look at step 3. So this is point C back to A. Okay, so right at the bat, since we know that our process is isothermal, we know that delta H and delta U are going to be equal to 0. Okay, so it's just a matter of calculating the work. Okay, so reversible work, this is going to be equal to negative nRT ln V2 over V1. Okay, so we have 1 mole, and our R is 8.314 joules per mole Kelvin. Our temperature for the isotherm is 200 K, and our change in volume is, okay, so we're compressing our gas back to the original state. Okay, so 4.103 liters, 16.412 liters is our initial. So calculating our reversible work, this gives us 2305 joules. Okay, so it makes sense that it's positive because we are compressing the gas back to its original state. Okay, so Q is just going to be the opposite of this, so it's just going to be negative 2305 joules. All right, so we calculated all of the parameters for each step. So now let's tabulate it and also calculate the overall process. Okay, so let's look at the step here. Okay, so we're going to go from A to B, B to C, and then C to A, and then we'll sum up everything to get the overall process. Okay, so let's tabulate Q, W, delta U, and delta H. Okay, so let's just recall the values that we got for each of these steps. Okay, so for Q over here, we got 17459 joules. Okay, same thing for our enthalpy. Okay, so for our internal energy, we got 12471 joules. For our work, however, we got negative 4988 joules. Okay, so always a good way to double check everything is to make sure that when we sum Q and W, it's equal to delta U. Okay, so for our isochoric process, our work is equal to 0. Okay, our change in internal energy is negative 12471 joules, which is equal to our heat at constant volume. And we also have our corresponding change in enthalpy, which is negative 17459 joules. For our isothermal process, we had 0 for both of the change in internal energy and our change in enthalpy, and our work was 2305 joules, and our heat was negative 2305 joules. Alright, so let's look at the overall. Okay, so first let's look at the change in internal energy and the change in enthalpy. Okay, so note that we're just going to sum all of this, and hey, it ends up being 0 for both of them. Okay, so why does it make sense that for the overall process okay, delta U and delta H are 0. Okay, so let's look at the overall process. We started with point A, right? And then we ended up with point A. Okay, so overall we just go from A to A, so there's not really a change in our state here. Okay, so that makes sense that our overall process is just 0 for both cases. Okay, so this makes sense because they're state functions, right? So it just depends on the final and the initial states, and it just so happens that for a cyclic process, the final and the initial states are the same. Okay, so there's no change. Okay, so now let's look at our path functions, our non-state functions, Q and W. So summing all of this together, okay, so summing our work, we get negative 2683 joules, okay? And then next one will something interesting if we add up all of these here. We get positive 2683 joules. Okay, so what do we notice about these two values? They're equal in magnitude but opposite sign. Okay, so why does it make sense that this is true? Okay, so note that for the overall process, delta U for the overall process is 0. So that means that the heat and the work for the overall process, upon adding them together, they should also be equal to 0. Okay, so again, this is a very, very nice way to double check your work, okay, if you're calculating for cyclic processes. Okay, so double check that Q plus W is equal to your delta U, and for the overall processes, your delta U and your delta H should be equal to 0, and that the sum of your overall heat and work should also be equal to 0. Okay, so again, this also emphasizes the difference between state and non-state functions. Okay, so for state functions, okay, it just depends on the final and initial state, right? But for non-state functions, it actually depends on what you ended up doing in the overall process. Okay, so you ended up doing work, right? Even though you end up with the same place. And you ended up inputting heat, even though you ended up in the same place in the overall process. Okay, so keep in mind again, guys, that all of the equations that we just used, this applies for ideal gas only. So once we start talking about chemical reactions and for phase changes, this is when the story changes a little bit, okay? But keep in mind that the same basic thermodynamic principles are always going to hold, okay? So with all this in mind, now let's look at other processes, okay, such as chemical reactions, phase changes, okay? So this is our interest when we start looking at thermochemistry, okay? Okay, so in thermochemistry, we're interested in studying the heat transfer involved in physical and chemical processes. Okay, so we usually encounter these processes during constant pressure conditions. Okay, so we can easily measure these types of things in the lab, for example. Okay, so currently we're under constant pressure conditions of our atmospheric pressure, okay? So again, if we're measuring heat at constant pressure, this is immediately correlated with enthalpy. Okay, so that's why enthalpy is very, very convenient, because if ever we measure heat at constant pressure conditions, this is already correlated with a state function. Okay, so just as a review, okay, we know that if enthalpy is negative, this is an exothermic process, and if it's positive, it's an endothermic process, okay? So an important part in thermochemistry is our thermochemical equation, okay? So this is just a balanced chemical equation with the heat involved at a particular temperature and pressure, okay? So usually it's written as so, okay, so we have an enthalpy value here next to the balanced chemical equation, okay? So in this particular case, we have this little knot here, okay? So what does this knot here refer to? Okay, so this actually refers to our standard pressure conditions, okay? So that is 1 bar, or in some old school textbooks, it still refers to it as 1 atmosphere, okay? So note that I only said it refers to a standard pressure, okay? So it does not actually refer to any standard temperature, okay? So this knot here just means that this process was measured at 1 bar or 1 atmosphere. So it does not refer to a temperature in particular. Okay, usually, however, we do encounter it to be 25 degrees Celsius, but not always. Okay, so this enthalpy could refer to another temperature, okay? However, if it's not indicated, you could probably assume that it's for 25 degrees Celsius. But it's important to actually indicate what temperature it refers to. Okay, so let's look at additional properties. Okay, so note that the phases must be indicated for our thermochemical equation. Okay, so if ever we change the phase, we also need to take into account the enthalpy of the phase change for that process, which will in turn affect the enthalpy for the entire process as written here. Okay, so the temperature again of the reaction must be indicated. Okay, so if not, you could probably assume that it's 25 degrees Celsius. Okay, and also note that enthalpy is an extensive property. Okay, so what does this per mole thing here refer to, by the way? Okay, so this per mole for this enthalpy over here as written, this refers to per mole of the entire reaction as written. Okay, so that means if we multiply this whole equation by 2, so say that we have 2 hydrogen plus 1 oxygen yielding 2 water, okay, so we need to multiply this whole thing by 2 as well. Okay, so additional things to keep in mind as well is that for a reverse process, the sign is also going to be reversed. Okay, so if we're looking at the decomposition of water to form hydrogen and oxygen gas, okay, so the enthalpy is now going to be positive instead of negative. Alright, okay, so we could also relate enthalpy and change in internal energy based on the process's pressure, volume, work. Okay, so overall we defined enthalpy as delta U plus P delta V. Okay, so this is like the pressure volume work done by your system. Okay, so typically we see pressure volume work to be significant if we have gases involved. Okay, so if you have liquids and solids involved, usually the volume changes are not significant. Okay, so if only solids and liquids are involved in a reaction, typically delta H is very close to delta U, okay, because the volume changes that occur in these types of processes are not very significant. However, if we start dealing with gases, that's when the story starts to change, okay? So you could imagine your beaker here, okay, so say that you have a solution and then one of your products happens to be a gas. Okay, so note in our laboratory conditions or in conditions right now, okay, we always have our atmospheric pressure pushing against the system here. Okay, so if our reaction happens to produce a gas, okay, so if this gas is going to escape, it's going to be pushing against this atmospheric pressure. Okay, so this is your pressure volume work. Okay, so we could look at this in terms of the number of moles of gas that is produced in our reaction versus that of the reactants. Okay, so we could write P delta V as delta NGRT. Okay, so typically the reactions that we're interested in are going to be occurring at constant pressure and constant temperature. Okay, so the pressure volume work that's going to be done is based on the change in the number of moles of gas that happens in the reaction. Okay, so delta Ng, this is going to be equal to the number of moles of gas in the products minus the number of moles of gas in the reactants. Okay, so we could write delta H as delta U plus the change in number of moles of gas times RT. Alright, okay, so we could use this equation to relate delta U and delta H based on the change in number of moles of gas that we encounter. Okay, so again, keep in mind that we derive this equation using the ideal gas equation, so we're assuming that the gases involved behave ideally. Okay, so let's look at this example over here. Okay, so let's try to calculate delta U naught. Okay, so meaning change in internal energy at constant pressure of 1 atmosphere, and let's say that this occurs at 25 degrees Celsius. Okay, so calculating for delta U this time, we could rearrange the equation that we had earlier, and we will get delta H minus delta Ng RT. Okay, so delta Ng requires us to know how many moles of gas are produced. Okay, so this is just 1 mole of gas. Okay, and then in the reactant side, however, we have 1.5 moles of gas. Okay, so say that you have all of your reactants in a balloon. Okay, so you have a very large volume, so this is 1.5 moles of gas. Okay, however, if all of the hydrogen and the oxygen gas reacted to form your water, okay, so assuming that they're all contained within the same balloon over here, okay, so we just have 1 mole of gas then. Okay, so the volume of our balloon is going to get smaller. So you have a contraction process that's going on over here. Okay, so in this particular case, delta U naught, this is going to be equal to negative 16.3 kilojoules per mole. So the change in number of moles of gas is from 1.5 mole to 1 mole. So this is negative 0.5 moles of gas. Okay, times R. So let's use 8.314 times 10 to the negative 3 kilojoules per mole Kelvin, and our temperature is 298.15 Kelvin. Okay, so if we calculate delta U, this is going to be equal to negative 15.1 kilojoules per mole. Okay, so delta U takes into account any pressure volume work that was done during the process. All right, so not very convenient since you need to determine the amount of work that your system actually did. Whereas your enthalpy, it just really cares about the heat at constant pressure. All right, so now let's look at how we could actually measure these heats, okay? So we just use calorimetry, which is our method of measuring heats involved in chemical and physical processes just by monitoring temperature differences. So a major tool that we use in calorimetry is our calorimeter, okay? So we treat our calorimeter as an isolated adiabatic system, so that means all of the heats involved inside the calorimeter just stays inside, okay? So the sum of all of the heats should be equal to 0. Okay, so say that this red part over here is our system of interest and it just so happens to release some heat. Okay, so this heat is going to go into the other part of the calorimeter, the blue part over here. So your calorimeter is going to be absorbing this heat here. Okay, so we could measure this heat flow via a thermometer. Okay, so you can measure the temperature changes that occurs due to these processes. Okay, so typically, water is used as a very common heat sink or a heat source for the process being studied. Okay, so if water is being used, okay, so it's going to end up absorbing all the heat if our process of interest releases heat, or it's going to be a heat source if the process of interest needs to absorb heat. Okay, so we could use Q is equal to MC delta T to correlate any temperature changes with the heat flow involved with our material. Okay, so for water, our specific heat capacity is 4.184 joules per gram degree Celsius. Okay, so degree Celsius could also be in terms of Kelvin. Okay, so we could also see this in terms of calorie. Okay, so the specific heat capacity of water is just 1 calorie per gram degree Celsius. Okay, so you kind of see where the calorie came from. It actually came from the thermal properties of water. Okay, sometimes, however, we just use the entire calorimeter as the heat sink or the heat source. Okay, so in this particular case, we could just use the calorimeter constant to correlate the changes in temperature with the corresponding heat flow within the calorimeter. Okay, so we have two major types of calorimeters. Okay, so one type is a bomb calorimeter. Okay, so this measures heat at constant volume. Okay, so note that there is a specialized setup over here, a sealed so-called bomb that makes sure that the volume remains constant during the entire process. Okay, so since we have constant volume, that means any heat involved is our QV. Okay, which can be directly related to changes in internal energy. Okay, so again, in bomb calorimetry, the type of heat that you are measuring can be correlated directly to delta U. So while it's convenient that we could immediately get the change in internal energy using a bomb calorimeter, okay, of course you need this specialized setup. Okay, commonly encountered and humble setup, however, is your so-called coffee cup calorimeter. Okay, so this is your calorimetry at constant pressure conditions. Okay, so the setup is very, very simple. You just have a coffee cup or some sort of insulating container, and then you could have your reaction occurring here, and you could monitor the temperature using a thermometer. Okay, so again, the heat that you would measure here would be your QP. Okay, so heat at constant pressure, which can be immediately correlated with changes in your enthalpy. If, however, you're interested in calculating delta U, you could use the relationship between delta H and delta U, however. Okay, so let's try to solve this calorimetry problem really quickly. Okay, so in our particular example, we have a sample of magnesium that is burned in a constant pressure calorimeter. Okay, so we're given the heat capacity of the calorimeter, and we're also given the temperature change of the calorimeter. Okay, so we just want to calculate the enthalpy of combustion of magnesium. Okay, so the combustion reaction is written as follows here. Okay, so since we're dealing with a calorimeter system, we know that the total heats involved in the calorimeter are all going to be equal to 0. So it's just a matter of figuring out what the heats are involved in the calorimeter. Okay, so we have Q reaction. Okay, so this is the heat released by the combustion reaction, and we also have Q cal. Okay, so this is all going to be equal to 0. Okay, so we just have two major components of heat flow in our calorimeter. Okay, so we could write this as Q reaction as equal to negative Q cal. Okay, so let's just expand these terms. Okay, so this is going to be N delta H combustion, okay, which is equal to negative C cal delta T. Okay, so solving for the enthalpy of combustion, okay, so this is going to be equal to negative C cal delta T divided by N. Okay, so N in this case is going to be the number of moles of magnesium. Okay, so we can use magnesium as a basis for the moles of reaction. Okay, so since there is a one-to-one correspondence of the moles of magnesium and the moles of reaction as written. Okay, so let's input all the values over here. So you can input the value for C cal. Okay, so let's just put this in terms of kilojoules. So this is going to be 5.760 kilojoules per degree Celsius. Okay, and our change in temperature, which is positive 0.570 degrees Celsius, divided by the number of moles of magnesium. So we're given the mass over here, 0.1326 grams of magnesium. So let's just convert this number of moles times 1 mole of magnesium divided by 24.305 grams. Okay, so calculating the enthalpy of combustion will give us negative 602 kilojoules per mole reaction. All right? Okay, so now let's look at another way to calculate the enthalpy changes of different processes. Okay, so while calorimetry works very well, the issue with that is that you need to do experiments, and sometimes you just want to save time and calculate things that don't need to be measured directly. Okay, so we could use Hess's law, which takes advantage of the fact that enthalpy is a state function. Okay, so we can just use alternative pathways in order to calculate the enthalpy of certain processes. Okay, so here's an illustration of Hess's law. Okay, so say that we have one reaction, A plus B yielding C, and we have a corresponding enthalpy for that. Okay, and then we can sum this with another reaction in order to calculate the enthalpy of another reaction over here. Okay, so the enthalpy of X plus B yielding Y is just going to be the enthalpy of reaction 1 plus reaction 2. Okay, so this is the basic principle of Hess's law. Okay, so we could also use another special application of Hess's law by using so-called standard formation reactions. Okay, so the standard enthalpy of formation corresponds to a formation reaction. Okay, so a formation reaction corresponds to the formation of 1 mole of a compound from its elements in their standard states at 1 atmosphere. At a specified temperature again. Okay, so usually the temperature is 25 degrees Celsius, but you just have to double check what temperature it refers to. Okay, so again, keep in mind that you have to form 1 mole of your substance from the elements in their standard states. Okay, so for example, the standard state of carbon is graphite, and you need 6 moles of this to form 1 mole of your benzene, and you need 3 moles of your hydrogen gas to form 1 mole of your benzene. Okay, so this reaction corresponds to this enthalpy over here. Okay, so what we can do here is that in order to calculate the enthalpy of a reaction of interest, okay, so we could just use these tabulated values and calculate the enthalpy of the reaction. Okay, so it's just going to be the sum of the enthalpy of formations, of the products times the corresponding number of moles minus the sum of all the enthalpy of formation of the reactants times the corresponding number of moles. Okay, so let's try to apply Hess's law using this particular problem. Okay, so we're given the standard enthalpies of formation of carbon dioxide, benzene, and water. Okay, but we want to calculate the enthalpy of combustion of benzene. Okay, so in addition, we also want to calculate the change in internal energy of combustion at 298.15 Kelvin. Okay, so before we begin, we need to have a balanced chemical equation. Okay, so let's write down the combustion reaction of our benzene. Okay, so benzene plus oxygen gas is going to yield our typical products. Okay, so carbon dioxide gas, okay, and our water in the liquid state. Okay, so let's just balance this equation over here. Okay, so we need 3 moles of water for every mole of benzene. We need 6 moles of carbon dioxide for every mole of benzene. And in order to combust this completely, we should have 15/2 moles of oxygen. Okay, so in order to calculate the enthalpy of combustion, it's just products minus reactants. Okay, so for the products, we have 6 moles of CO2 per mole of reaction as written. Okay, so this is times negative 393.51 kilojoules per mole of CO2 plus 3 moles of H2O per mole reaction times the enthalpy of formation. So this is negative 285.83 kilojoules per mole. Okay, minus the reactants. Okay, so we have 1 mole of benzene per mole reaction as written here times the enthalpy of formation of benzene. So kilojoules per mole benzene. And note that we don't have an enthalpy of formation of oxygen. Okay, so just for emphasis, let's write down the formation reaction of oxygen. Okay, so this is going to be oxygen gas. Okay, so this is just going to form oxygen gas, right? Okay, so the formation of 1 mole of compound from its standard state. So the standard state of oxygen is just oxygen gas, right? So that means no change has occurred. So that means enthalpy of formation of oxygen is just going to be 0, right? Okay, so this is pretty much true for all other elements in their standard states. Okay, so this is just 15 halves of oxygen per mole of reaction, so 15 halves mole oxygen times 0. Okay, so overall, if we calculate the enthalpy of combustion, this will give us negative 3,267 kilojoules per mole reaction. Okay, so this is our enthalpy of combustion. Okay, so if we want to calculate the change in internal energy at 25 degrees Celsius, this is just going to be the heat involved in the process minus delta NG/RT. So the change in number of moles of gas, guys, are going to be 6 minus 15/2. Okay, so if we calculate this at 298.15 K, we should just get negative 3263 kilojoules per mole as our change in internal energy. Okay, so note that water in this particular reaction as written is in the liquid state, so it doesn't count towards the change in number of moles of gas. Okay, so there we have our problem here. Okay, so this is an application of Hess's law. Right? So let's look now at the temperature dependence of enthalpy changes. So previously we talked about the temperature dependence of our heat capacity. So this is also going to come into play once we start looking at enthalpy changes at different temperatures. Okay, so for the most part, we've been dealing with processes that occur at around 25 degrees Celsius, right? Okay, however, we have to keep in mind that there's going to be a temperature dependence of these enthalpy changes that we're investigating. Okay, so for example, if you want to know the enthalpy change at 1000 Kelvin, okay, it's not necessarily going to be the same thing as the value that we calculated at 25 degrees Celsius. So another consideration that we have to look at is the possible phase changes of the substances that we're dealing with. Okay, so for example, at different temperatures, it could exist as a solid, liquid, or a gas. Okay, so you need to take into account the different heat capacities of the substance in those different phases. And you might also have to take into account the different enthalpies of phase changes that could occur for those substances at different temperatures. All right, so let's look at phase changes first. Okay, so we could have vaporization and fusion of our substances. Okay, so they have a corresponding enthalpy. Okay, so for the most part, if you see this little knot over here, this means that we're looking at the enthalpy of vaporization or the enthalpy of fusion at 1 atmosphere, okay, or standard pressure. Okay, so usually the temperature at which these processes occur are at the corresponding boiling point and the melting point. Okay, so we're looking at the normal enthalpies of vaporizations and the normal enthalpies of fusion. Okay, however, we could actually calculate for these phase change enthalpies at different temperatures. Okay, so how are we going to do that? Let's try that with the next example over here. Okay, so for this particular example, we want to calculate the heat required to vaporize 1 mole of liquid water at 25 degrees Celsius. Okay, so just for emphasis, this is all occurring at 1 atmosphere, okay, so all at constant pressure conditions. Okay, so let's look at the process that we're interested in. Okay, so we want to vaporize 1 mole of water at 25 degrees Celsius. So we have liquid water at 25 degrees Celsius being converted at constant temperature to gaseous water at 25 degrees Celsius. Okay, so again, always keep in mind that phase changes, they always occur at constant temperature conditions. Okay, so we want to figure out the heat involved for this process, but the only thing that we have here is the enthalpy of vaporization at the normal boiling point of water. Okay, so what we do have is liquid water at 100 degrees Celsius forming our gaseous water again at 100 degrees Celsius. Okay, this is the process that we're interested in, but keep in mind again that since we're dealing with heats at constant pressure, this is equal to just enthalpies, right? So enthalpy is a state function. So since enthalpy is a state function, that means we could find alternative pathways for the process of interest in order to calculate for the corresponding enthalpy for that process. Okay, so instead of getting the direct pathway of converting liquid water at 25 degrees Celsius to water vapor at 25 degrees Celsius, what we can do is first we could increase the temperature of liquid water to the boiling point from 25 degrees Celsius, vaporize it, and then we could bring the temperature back down to 25 degrees Celsius, right? Okay, you can see what we did here. Okay, so this is the direct pathway. Okay, so you don't really know the exact value for this. However, an alternative but equivalent pathway would be the long way around. Okay, increasing the temperature, okay, vaporizing it at the normal boiling point, and bringing the temperature back down to 25 degrees Celsius. Okay, so even though it's a long way around, this is a thing that we could actually calculate. Okay, so Q1, okay, so the heat involved in raising the temperature, this is just going to be NCP of liquid water times the change in temperature. Okay, so Q2, okay, so this is the vaporization of 1 mole of water at 100 degrees Celsius. This is just going to be N delta H VAP. Okay, at 100 degrees Celsius. Okay, so Q3, okay, this is just going to be NCP of gaseous water delta T. Okay, so we're bringing down the temperature of gaseous water back to 25 degrees Celsius. Okay, so overall, our Q net, this is going to be the heat involved in vaporizing 1 mole of water at 25 degrees Celsius. Okay, we can calculate all of this over here. Okay, and then we'll get NCP delta T. Okay, so this is for water in the liquid phase, plus N delta H vap, okay, plus N Cp for gaseous water and the change in temperature here. So let's plug in all the values. Okay, so this will give us Q net is equal to, okay, so 1 mole heat capacity of liquid water, 75.4. Okay, so let's put this in terms of kilojoules, so times 10 to the negative 3 kilojoules per mole Kelvin. Change in temperature, okay, so we're bringing it from 25 to 100 degrees Celsius. Okay, so our change in temperature is 75 degrees Celsius. Okay, but keep in mind that differences in temperature in the degrees Celsius scale is going to be equivalent to changes in temperature in the Kelvin scale. So we could write our temperature difference as 75 Kelvin. Okay, so for heat number 2, we have 1 mole, okay, times the enthalpy of vaporization at 100 degrees Celsius. And then we have our heat number 3, which is bringing down the temperature of our gaseous water back to 25 degrees Celsius. Okay, so heat capacity of gaseous water, kilojoules per mole, Kelvin. Okay, and then we're bringing down the temperature, so it's negative 75 Kelvin. Okay, so if we calculate the net heat involved, we have 43.78 kilojoules. Okay, so this is the amount of heat required in order to vaporize 1 mole of water at 25 degrees Celsius. Okay, so note that at a lower temperature, it takes more heat in order to vaporize 1 mole of water. Okay, so at this lower temperature, okay, we have a larger enthalpy because we need to assist our water molecules at 25 degrees Celsius to escape the intermolecular force of attraction in order to vaporize. Alright, so this is for phase changes, so we could actually do something very similar for chemical reactions. So whenever we're looking at the enthalpies of certain reactions, we usually see them given at 25 degrees Celsius. Okay, so what happens, however, if we're interested in investigating the reaction at higher temperatures or lower temperatures? Okay, so we could actually try another technique that is very similar to what we did earlier for our phase changes. Okay, so we could find alternative pathways in order to calculate for the enthalpy of our reaction at another temperature. So for example, let's consider our reaction at 1000 Kelvin. Okay, so it's usually what's given to us is the enthalpy of reaction at 25 degrees Celsius. Okay, so again, this is the direct pathway for the reaction at 1000 Kelvin. We could devise an alternative pathway in order to get to the same final state. Okay, so what's available to us is data on enthalpy of the reaction, usually at 25 degrees Celsius. Okay, so we can devise an alternative pathway by taking our reactants at our desired temperature, which is 1000 Kelvin, and decrease the temperature to 25 degrees Celsius. Okay, so this is done with the corresponding heat capacities of our reactants A and reactants B. Okay, so once our reactants are at 25 degrees Celsius, okay, so the reaction can proceed as usual, involving the enthalpy of the reaction at 25 degrees Celsius, and then we produce our products again at 25 degrees Celsius. Okay, so the next step to connect these points is to increase the temperature of our products to the desired temperature of 1000 Kelvin. Okay, so again, this is going to involve the heat capacities of our products. Okay, so it's pretty much the same strategy that we used for our earlier example. We just found an alternative pathway in order to calculate the enthalpy of interest using the data that we have on hand. Okay, so we could get a shortcut for the relationships between the enthalpy of the reaction at different temperatures by using the properties of enthalpy that we know. Okay, so since we're dealing with reactions, we are dealing with the enthalpy of reaction, which is just the enthalpy of the products minus the enthalpy of the reactants. Okay, so again, we're interested in temperature dependence, right? So we want to see how this enthalpy is going to change with varying temperature. Okay, so that means we're interested in getting the derivative of this entire expression with respect to temperature at constant pressure. Okay, so what we're going to do here is I'm going to get the partial derivative of these enthalpies with respect to temperature at constant pressure. Partial derivative of the enthalpy of the reaction with respect to temperature at constant pressure, this is going to be equal to the partial derivative of the enthalpy of the products with respect to temperature at constant pressure minus the partial derivative of the reactants with respect to temperature at constant pressure. Okay, so we could express these terms over here with another expression that we are familiar with. Okay, so note before that we defined dH as NCP dt. Okay, so we could do some rearrangement, okay, and then we could write down the partial derivative of enthalpy with respect to temperature at constant pressure as NCP. Okay, so let's replace all of these terms over here, this term and this term, with NCP. Okay, so keep in mind that this is the enthalpy of the sum of the products, the enthalpy of the sum of the reactants. Okay, so this means that we'll be looking at N of the products times the CP of the products minus the number of moles of the reactants, the CP of the reactants. Okay, so keep in mind that we're getting the summations of all of this here. Okay, so we could symbolize this over here as delta CP. Okay, so delta CP, this is a CP of the products times its corresponding number of moles minus the CP of the reactants times the corresponding number of moles. Okay, so this is equal to the partial of the delta H of the reaction with respect to temperature at constant pressure. Okay, so actually this relationship over here, this is given a special name. This is called Kirchoff's rule. Okay, so this tells us the variation in temperature of our enthalpies. Okay, so how are we going to use Kirchoff's rule? Okay, so upon evaluation of this, we have this partial derivative, right? Okay, so partial derivative, again, this is just a ratio of differentials. So we could always rearrange these differentials. Okay, so let's bring up the dt to the other side. Okay, so after this, we'll have d delta H is equal to delta CP dt. Okay, so with this, we could do some integration. Okay, so we could integrate this from the temperature, from temperature 1 to temperature 2, and then we'll be integrating this side over here from delta H at temperature 1 to delta H at temperature 2. Right? So upon integration, we have delta H at temperature 2 minus delta H at temperature 1 is equal to this integral over here, delta Cp dt. Okay, so you just have to be a little careful because sometimes our delta Cp has a temperature dependence. Okay, so overall, our equation is delta H at temperature 2 is equal to delta H at temperature 1 plus this integral over here, temperature 1, temperature 2, delta Cp dt. Okay, so what is this temperature 1 over here, this enthalpy at temperature 1? So this is usually our reference temperature. Okay, so for example, if you have the enthalpy at 298 Kelvin, this serves as your reference. Okay, so you could use this as a basis in order to calculate for the enthalpy at a higher temperature at T2. Okay, so 298 in this particular example is going to be equal to our T1. Okay, and the temperature of interest is going to be equal to our T2. Okay, so actually this whole equation here, this is equivalent to the alternative pathway technique that we did here. So the integral of our delta Cp dt, this takes into account the raising and the decreasing in temperature of our products or reactants, okay, to the desired temperature. Okay, so this over here, this is the reference enthalpy that we use in order to calculate the enthalpy at the higher temperature. All right. So again, so note how careful we were about keeping this in the integral form. Okay, so this is important, especially we have to keep in mind the temperature dependence of our heat capacities. Okay, so with these all in mind, let's try to solve this problem over here. So we know that the standard molar enthalpy of formation of ammonia gas is negative 46.11 kilojoules per mole. Okay, so this is at 25 degrees Celsius. So using the heat capacity data given below, we want to calculate the standard molar heat of formation of ammonia at 1000 Kelvin this time. Okay, so first things first, we need a balanced chemical equation. Okay, so we're looking at the formation reaction of ammonia. So that means we just need half a mole of nitrogen gas and 3/2 of a mole of hydrogen gas in order to form 1 mole of ammonia. All right, so next we need to find out what our delta Cp is. Okay, so we could write our delta Cp as delta Cp naught to indicate that the pressure is at our standard pressure. Okay, so our delta Cp, this is going to be equal to, okay, so for our products, we have 1 mole of ammonia. Okay, so we want to get the Cp of ammonia. Okay, and then we're going to be subtracting, okay, 1/2 mole of nitrogen times the Cp of nitrogen plus 3/2 of a mole of the 3/2 of a mole of hydrogen gas times the Cp of hydrogen gas. So that will give us our delta Cp. Okay, so ultimately, let's add these things together over here. Okay, so for ammonia, we just need to multiply this by 1, right? Okay, so for hydrogen, okay, we need to multiply this by negative 3/2. Okay, so for nitrogen, we need to multiply this by negative 1/2 as well. Okay, so note that we'll be subtracting the Cp of nitrogen and the Cp of hydrogen. Okay, so this will give us delta Cp. Okay, so in order to be organized about this, it's useful to calculate this term by term. Okay, as in you take the first term, multiply it by negative 1/2, add it to the second term, which is multiplied by negative 3/2, and add the term over here, okay, times just 1. Okay, so this will give us negative 31.21 plus 30.88 times 10 to the negative 3 times temperature. Okay, so the units for this whole expression will be in terms of joules per mole Kelvin. Okay, so let's call this value over here A, and let's call this value over here B. Okay, so we could write our delta Cp naught as just A plus BT. Okay, so let's look at our next step. Okay, so our next step is to evaluate the enthalpy of the formation reaction at 1000 Kelvin. So this is going to be equal to the enthalpy of the formation reaction at 298 Kelvin plus the integral of A plus BT dt evaluated from temperature 1 to temperature 2. Okay, so temperature 1, this is our reference temperature, so this is 298 Kelvin. And T2, this is going to be 1000 Kelvin. Okay, so this will give us AT plus B over 2T squared. Okay, so evaluate this at 1000 Kelvin for the final state and 298 Kelvin for the initial state. Okay, so keep in mind that this is going to be in terms of joules per mole upon evaluation. So it's necessary to convert this to kilojoules. Okay, so this will be 1 kilojoule per 1000 joules. Okay, so upon evaluating our enthalpy at 1000 Kelvin, this will be negative 53.95 kilojoules per mole reaction. All right. Okay, so there we go. Okay, but keep in mind that we made an important omission once we started using Kirchoff's rule. Okay, so we're assuming that any of the products and the reactants that we're dealing with is not going to change in phase. All right, so just another precaution to take just in case we're using Kirchoff's rule. All right, so overall we talked about many applications of the first law of thermodynamics. Okay, so at first we defined what energy was, different methods of transferring energy and causing changes in our system. And we looked at very simple cases of energy transfers involving the ideal gas system. And later we started looking at thermochemistry in order to investigate heats involved in different chemical and physical processes. Okay, so lastly, we looked at temperature dependence of processes and we're able to calculate the enthalpies of different processes at different temperatures. Okay, so again, note that enthalpy is not independent of temperature, so we need to take into account any temperature dependence here. Okay, so overall, we've just been calculating different ways in order to account for the energy of our system during different processes. Okay, so note, however, that we haven't really addressed another issue, which is spontaneity of certain processes. While we could account for the different energies involved in a process, we haven't really addressed whether that process is actually going to happen or not. Okay, so that is going to be the next topic of our next lecture once we start talking about the second law of thermodynamics. Okay.